Imagine for a moment that you could zoom out far beyond the Earth, far beyond the solar system, and even beyond the Milky Way itself. You'd see something so vast, so incomprehensible, that it would make our galaxy feel like a single grain of sand on an endless beach. That something is the Laniakea Supercluster, a colossal structure in the universe that not only contains the Milky Way but also connects us to hundreds of thousands of other galaxies. What exactly is this supercluster, and how does it help us understand our place in the universe? Stick around, because this is about to blow your mind. Let's start with the basics. The Laniakea Supercluster isn't just a random collection of galaxies floating around in space. It's an interconnected web of galaxies bound together by the subtle but powerful pull of gravity. The name, Laniakea, comes from the Hawaiian words lani, heaven, and akea, immense, which translates to immense heaven. It's an apt name because this supercluster stretches over 500 million light-years across and contains about 100,000 galaxies. For comparison, the Milky Way, our home galaxy, is a single galaxy within this incomprehensibly massive structure. But what makes the Laniakea Supercluster so special? The answer lies in its structure. To understand it, let's rewind to 2014, when a team of scientists led by R. Brent Tully at the University of Hawaii made a groundbreaking discovery. They mapped the movements of thousands of galaxies, looking at how they were influenced by gravity. What they found was astonishing. Galaxies in this region weren't just moving randomly. Instead, their movements were guided by a kind of gravitational flow, all converging toward a central point called the Great Attractor. The Great Attractor is one of the most mysterious parts of the Laniakea Supercluster. It's a massive region of space that seems to be pulling galaxies toward it with immense gravitational force. Scientists still don't fully understand what it is or why it's there. Some theories suggest it could be a dense cluster of galaxies or even a concentration of dark matter. Whatever it is, it acts as the central hub of the Laniakea Supercluster, drawing in galaxies like a cosmic drain. Now, here's where things get even more mind-boggling. The Laniakea Supercluster isn't isolated. It's part of an even larger structure, what some scientists call the cosmic web. This web is made up of filaments of galaxies and dark matter, stretching across the universe like a giant spiderweb. Between these filaments are vast voids, regions of space with hardly any matter at all. The Laniakea Supercluster is just one node in this enormous web, which connects superclusters across the universe. What's fascinating is how interconnected everything is. The Milky Way isn't just sitting still in the universe. It's moving, along with the rest of the Laniakea Supercluster, toward a region called the Shapley Supercluster, one of the densest concentrations of galaxies in the known universe. This movement is part of a larger pattern of cosmic flows, which show us that the universe isn't static. It's constantly evolving, with galaxies and superclusters shifting and merging over billions of years. To really grasp the scale of the Laniakea Supercluster, let's break it down. Our solar system is about 26,000 light-years from the center of the Milky Way. The Milky Way itself is about 100,000 light-years across. The local group, which includes the Milky Way and its neighboring galaxies like Andromeda, is about 10 million light-years across. The Virgo Supercluster, which the local group is part of, spans about 110 million light-years. And then there's Laniakea, dwarfing them all at over 500 million light-years. These numbers are so huge that they're almost impossible to comprehend. But they give us a sense of just how small we are in the grand scheme of things. One of the most intriguing aspects of the Laniakea Supercluster is how it challenges our understanding of the universe. For decades, scientists have tried to map the large-scale structure of the cosmos, but it's a daunting task. The universe is vast, and much of it is hidden from view. Telescopes can only capture a tiny fraction of the light emitted by distant galaxies, and dark matter, which makes up about 85% of the universe's mass, doesn't emit light at all. Yet, through clever techniques like measuring the redshift of galaxies, which tells us how fast they're moving away, and mapping gravitational flows, scientists have pieced together a rough map of our cosmic neighborhood. What's even more mind-blowing is that the Laniakea Supercluster might just be the beginning. Some scientists believe there could be even larger structures out there, beyond what we can currently observe. These megaclusters, or superclusters, would make Laniakea look tiny in comparison. It's a humbling thought, even our immense heaven might be just a small piece of a much larger puzzle. Another fascinating aspect of the Laniakea Supercluster is how it helps us understand the role of dark energy in the universe. Dark energy is the mysterious force driving the expansion of the universe. While gravity pulls galaxies together, dark energy pushes them apart. The balance between these forces determines the structure of the universe. In regions like the Laniakea Supercluster, gravity dominates, creating dense clusters of galaxies. But in the vast voids between superclusters, dark energy takes over, driving galaxies further apart, and creating the large-scale structure we see today. So, what does all of this mean for us? On one level, it's a reminder of how tiny and insignificant we are in the grand scheme of things. Our entire galaxy, with its billions of stars and planets, is just one tiny part of the Laniakea Supercluster. And the Laniakea Supercluster is just one tiny part of the universe. Yet, at the same time, it's a reminder of how interconnected everything is. The movements of galaxies billions of light-years away affect us, just as our own galaxy contributes to the larger cosmic dance. As we continue to study the Laniakea Supercluster, we're likely to uncover even more mysteries. What is the Great Attractor? How do dark matter and dark energy shape the structure of the universe? And what lies beyond the edges of our observable universe? These are questions that scientists are still working to answer, and each new discovery brings us one step closer to understanding the true nature of the cosmos. This interconnectedness, the way galaxies, superclusters, and the cosmic web are woven together, isn't just a scientific curiosity, it's a profound reminder of how much there is left to explore. The Laniakea Supercluster is an extraordinary case study in the complexity of the universe, but to truly appreciate its significance, we have to dig even deeper into its structure, its movements, and its implications. Let's return to the Great Attractor, the mysterious gravitational focal point of the Laniakea Supercluster. To visualize this, imagine the galaxies within Laniakea as rafts floating on a vast ocean, with the Great Attractor being a whirlpool pulling them inward. Scientists have determined that the gravitational pull of the Great Attractor is so immense that even our local group of galaxies, including the Milky Way, is caught up in its flow. This pull isn't happening at random, it's part of the intricate gravitational choreography that governs the universe. However, the Great Attractor is notoriously difficult to study because it lies in a region of the sky obscured by the Milky Way's dense disk of stars, gas, and dust. This area, known as the zone of avoidance, makes it challenging to observe objects directly in its vicinity. Despite this, scientists have used indirect methods, such as analyzing the velocities of galaxies and mapping their gravitational influences, to deduce the existence of the Great Attractor and its impact on our galactic neighborhood. Interestingly, the Great Attractor isn't the only force shaping the Laniakea Supercluster. Beyond it lies another massive structure, the Shapley Supercluster. This colossal region is one of the densest concentrations of galaxies ever observed, containing over 8,000 galaxies in a space about 650 million light-years across. While the Great Attractor pulls galaxies inward, the Shapley Supercluster exerts its own gravitational influence, creating a tug-of-war that shapes the movement of galaxies within Laniakea. To truly appreciate the complexity of the Laniakea Supercluster, we have to consider the role of dark matter. Unlike normal matter, dark matter doesn't emit or absorb light, making it invisible to telescopes. Yet, its gravitational effects are crucial in holding galaxies and superclusters together. Without dark matter, the Laniakea Supercluster wouldn't exist. Scientists believe that massive filaments of dark matter act as the scaffolding of the cosmic web, guiding the formation and movement of galaxies. But how do we even know dark matter is there? One clue comes from the rotation of galaxies. Observations show that galaxies spin much faster than they should based on the visible matter they contain. This discrepancy suggests the presence of an unseen mass, dark matter, providing the extra gravitational pull needed to hold galaxies together. In the case of the Laniakea Supercluster, dark matter plays a critical role in binding its galaxies and directing their flows toward the Great Attractor. As we zoom out to larger scales, the picture becomes even more intricate. The Laniakea Supercluster is part of a vast network of superclusters connected by filaments of dark matter and separated by enormous voids. These voids, some stretching hundreds of millions of light-years across, are regions where matter is sparse, and gravity's pull is weaker. The contrast between dense superclusters and these empty voids creates the cosmic web, a structure that resembles a 3D spiderweb stretching across the observable universe. One of the most profound questions about the Laniakea Supercluster is how it fits into the larger story of the universe's evolution. Scientists believe that superclusters like Laniakea began to form shortly after the Big Bang, around 13.8 billion years ago. In the early universe, matter was distributed almost uniformly, with only tiny variations in density. Over time, gravity amplified these variations, pulling matter into clumps that would eventually become galaxies, clusters, and superclusters. The process of supercluster formation is still ongoing today. Galaxies within the Laniakea Supercluster continue to move, merge, and interact, reshaping the structure over billions of years. This slow but relentless evolution highlights the dynamic nature of the universe. Nothing is static, even the largest structures are in a constant state of flux. What's particularly exciting about studying the Laniakea Supercluster is how it helps us understand the fate of the universe. Right now, the universe is expanding, with galaxies moving away from each other due to the influence of dark energy. But within superclusters like Laniakea, gravity is strong enough to counteract this expansion, keeping galaxies bound together. Over time, as the universe continues to expand, these superclusters may become isolated islands in an ever-expanding cosmic ocean. In other words, while galaxies within Laniakea will remain gravitationally connected, the supercluster itself will drift further away from other parts of the universe. This raises a profound question: what will happen to the Laniakea Supercluster in the distant future? Will it remain as it is, or will it evolve into something entirely different? Some scientists predict that as galaxies within Laniakea continue to merge, the supercluster could become dominated by massive elliptical galaxies, with most of the smaller galaxies either absorbed or flung out into intergalactic space. Others speculate that dark matter and dark energy will play a decisive role in shaping Laniakea's ultimate fate. Another fascinating aspect of the Laniakea Supercluster is how it challenges our understanding of cosmology. Traditional models of the universe often assume that matter is distributed evenly on large scales. But structures like Laniakea reveal that the universe is far more complex, with regions of incredible density surrounded by vast emptiness. These observations force us to refine our models and rethink our assumptions about how the universe works. What makes the Laniakea Supercluster truly special is its ability to inspire a sense of wonder and curiosity. It's a reminder that, no matter how much we learn about the universe, there's always more to discover. Each new piece of the puzzle, whether it's the role of dark matter, the mystery of the Great Attractor, or the dynamics of galactic flows, adds to our understanding of the cosmos and our place within it. The interconnected nature of the Laniakea Supercluster also invites philosophical questions about humanity's place in the grand cosmic web. When you consider the sheer size and complexity of Laniakea, it becomes clear that our Milky Way, despite containing billions of stars, is just one small thread in this vast tapestry of galaxies. This realization can evoke both humility and awe. We are part of something unimaginably large, yet we exist on a tiny planet orbiting an ordinary star within a nondescript galaxy. And yet, from this vantage point, we have developed the tools to map, study, and begin to comprehend the structure of the universe. The name, Laniakea, which translates to immense heaven in Hawaiian, beautifully encapsulates this dual sense of wonder and perspective. The name was chosen to honor the Polynesian navigators who used their deep understanding of the stars to traverse vast oceanic distances. Just as those ancient explorers sought to map the seas, modern astronomers are charting the cosmic ocean, uncovering the structure of Laniakea and beyond. One intriguing aspect of the Laniakea Supercluster is the way its discovery reshaped our understanding of cosmic geography. Before 2014, astronomers categorized galaxies and galaxy clusters into smaller, separate structures, such as the Virgo Supercluster, to which the Milky Way was thought to belong. However, by studying the motion of galaxies and using a method called cosmic flow analysis, researchers realized that these smaller clusters are part of a much larger, unified structure, Laniakea. This breakthrough not only expanded our view of the universe but also underscored the importance of interconnectedness in understanding cosmic phenomena. Cosmic flow analysis involves tracking the movement of galaxies relative to the overall expansion of the universe. While galaxies are carried outward by the universe's expansion, their individual motions are influenced by local gravitational forces. By mapping these movements, scientists can identify the gravitational valleys and rivers that guide galaxies toward massive structures like the Great Attractor. In the case of Laniakea, this technique revealed a complex network of galactic streams converging toward a common center, redefining the boundaries of our galactic neighborhood. This discovery raises an important question: how many other superclusters like Laniakea exist, and how do they compare? Scientists estimate that there are millions of superclusters in the observable universe, each with its own unique structure and dynamics. Some are more densely packed with galaxies, while others are more spread out. Understanding these variations can provide valuable insights into the processes that shape the universe, from the Big Bang to the present day. The study of superclusters also has profound implications for understanding dark energy, the mysterious force driving the accelerated expansion of the universe. By examining the distribution and motion of superclusters like Laniakea, scientists can gain clues about how dark energy operates on the largest scales. For example, the fact that Laniakea remains gravitationally bound despite the universe's expansion suggests that dark energy is not uniform, but varies in strength across different regions of space. This idea, while still speculative, could revolutionize our understanding of one of the greatest mysteries in cosmology. Another area of research focuses on the role of magnetic fields within superclusters. While gravity is the primary force shaping the structure of the Laniakea Supercluster, magnetic fields also play a significant role in influencing the behavior of intergalactic gas and plasma. These magnetic fields, though weak compared to those found in galaxies, can stretch across millions of light years, affecting the formation of stars and galaxies. Studying these fields could help scientists understand the interplay between magnetic forces and gravity in shaping cosmic structures. The Laniakea Supercluster also offers a unique opportunity to study galactic interactions on a massive scale. Within Laniakea, galaxies are not isolated entities. They constantly interact, collide, and merge. These interactions can trigger bursts of star formation, fuel the growth of supermassive black holes, and even reshape galaxies entirely. By observing these processes within the context of a supercluster, scientists can gain a deeper understanding of how galaxies evolve over billions of years. One fascinating aspect of these interactions is the role of tidal forces. Just as the moon's gravity creates tides on Earth, the gravitational pull of nearby galaxies can distort and reshape one another. In some cases, these tidal forces can strip away gas and stars, creating long streams of material that stretch between galaxies. These tidal streams provide valuable clues about the history of galactic interactions and the distribution of dark matter within Laniakea. As we continue to study the Laniakea Supercluster, new technologies and techniques promise to reveal even more about its structure and dynamics. For example, next-generation telescopes like the James Webb Space Telescope and the upcoming Extremely Large Telescope are capable of observing distant galaxies in unprecedented detail, providing new data on the composition, motion, and evolution of galaxies within Laniakea. Additionally, advances in computer simulations allow scientists to model the formation and evolution of superclusters, testing hypotheses about their origins and behavior. Despite these advancements, there is still so much we don't know about the Laniakea Supercluster and the universe as a whole. What lies beyond its boundaries? How did its complex structure emerge from the relatively uniform conditions of the early universe? And what role will Laniakea play in the future evolution of the cosmos? These questions remind us that the universe is not a static, unchanging place, but a dynamic and ever-evolving entity, full of mysteries waiting to be unraveled. The exploration of the Laniakea Supercluster is a testament to humanity's curiosity and ingenuity. It shows that, despite our small size and limited perspective, we are capable of unlocking the secrets of the cosmos through observation, analysis, and imagination. It also highlights the importance of collaboration, as scientists from around the world work together to piece together the puzzle of our galactic neighborhood. Ultimately, the study of the Laniakea Supercluster is about more than just understanding the structure of the universe. It's about finding our place within it. By mapping the vast expanse of galaxies that surround us, we gain a deeper appreciation for the interconnectedness of all things and the delicate balance that sustains the cosmos. It's a reminder that, no matter how vast and overwhelming the universe may seem, we are an integral part of its story. The story of the Laniakea Supercluster is deeply intertwined with the forces that govern the universe, forces that have shaped its structure over billions of years. One of these fundamental forces is gravity, the invisible glue that binds galaxies, clusters, and superclusters together. Yet, gravity is only part of the story. The interplay between gravity and dark matter, the enigmatic substance that makes up most of the universe's mass, is crucial to understanding Laniakea's formation and evolution. Dark matter acts as a scaffolding for the universe, providing the gravitational framework within which galaxies form and cluster. While we cannot see or directly detect dark matter, its presence can be inferred through its gravitational effects on visible matter. Within the Laniakea Supercluster, dark matter plays a pivotal role in shaping the paths of galaxies as they flow toward the Great Attractor, the region of immense gravitational pull at the heart of Laniakea. The Great Attractor itself is one of the most mysterious regions in the known universe. Its precise nature remains unclear, but it is thought to be a massive concentration of galaxies, dark matter, and other cosmic material. Observing the Great Attractor is challenging because it lies behind the zone of avoidance, a region of space obscured by the Milky Way's dense disk of stars, gas, and dust. Despite this obstacle, astronomers use indirect methods, such as measuring the velocities of galaxies and the distortion of light due to gravitational lensing, to study this enigmatic region. What makes the Great Attractor even more fascinating is the way it influences galaxies far beyond Laniakea's boundaries. Its gravitational pull extends over hundreds of millions of light-years, drawing galaxies from neighboring superclusters and contributing to the larger cosmic web. This interconnectedness suggests that Laniakea is not an isolated structure but part of a much larger and more intricate network of superclusters, clusters, and voids. Void regions, which are the vast, nearly empty spaces between clusters and superclusters, are another key feature of the Laniakea Supercluster. These voids are not entirely devoid of matter but contain extremely low-density gas and the occasional galaxy. They serve as the backdrop against which the luminous threads of the cosmic web are woven. Studying these voids can reveal important clues about the distribution of dark energy, the force driving the accelerated expansion of the universe. Dark energy is perhaps the greatest puzzle in modern cosmology. It accounts for approximately 70% of the universe's total energy content and is thought to counteract gravity on the largest scales, pushing galaxies and superclusters apart. Yet, the exact nature of dark energy remains elusive. By examining structures like Laniakea, scientists hope to better understand how dark energy interacts with gravity and influences the universe's large-scale structure. The existence of Laniakea also prompts questions about the early universe. How did this vast supercluster come into being? The answer lies in the cosmic microwave background radiation, the faint afterglow of the Big Bang. This radiation provides a snapshot of the universe when it was just 380,000 years old, revealing tiny fluctuations in density that eventually grew into the galaxies and superclusters we see today. These fluctuations were amplified by gravity, creating the intricate web of matter that forms the backbone of Laniakea and other cosmic structures. As we continue to explore Laniakea, new discoveries constantly challenge our understanding of the universe. For instance, the discovery of ultra-diffuse galaxies, large galaxies with very few stars, within superclusters has raised questions about how these faint objects form and survive in such dynamic environments. Some of these galaxies are so diffuse that they appear almost ghostly, with their stars spread out over enormous distances. Understanding their origins could shed light on the processes that shape galaxies within superclusters. Another area of active research is the role of cosmic filaments within Laniakea. These filaments, which connect clusters and superclusters, are the highways along which galaxies and matter flow. They are thought to be the sites of intense star formation and galaxy interactions, making them critical to the evolution of the cosmic web. By studying these filaments in detail, scientists can uncover the mechanisms that drive galaxy growth and the redistribution of matter in the universe. The study of Laniakea also has practical implications for understanding our own galaxy's future. The Milky Way is currently on a collision course with the Andromeda Galaxy, a massive spiral galaxy that is also part of Laniakea. This event, expected to occur in about 4.5 billion years, will reshape both galaxies, creating a new elliptical galaxy in their place. Understanding how galaxies interact and merge within the context of a supercluster can provide valuable insights into what the Milky Way-Andromeda collision might look like and its long-term consequences. As technology advances, our ability to study Laniakea and other superclusters will continue to improve. The next generation of telescopes, such as the Square Kilometre Array (SK) and the Vera-C Rubin Observatory, promises to revolutionize our understanding of the universe's large-scale structure. These instruments will allow astronomers to map the distribution of galaxies and dark matter with unprecedented precision, uncovering new details about Laniakea's composition and dynamics. Despite these advancements, many questions remain unanswered. What lies beyond the boundaries of Laniakea? Are there larger structures, such as hyperclusters, that encompass multiple superclusters? How do the processes within Laniakea compare to those in other superclusters? These questions highlight the vastness of what we have yet to learn and the excitement of exploring the unknown. The Laniakea Supercluster is more than just a collection of galaxies. It is a window into the fundamental forces and processes that shape the universe. It challenges us to think on scales that defy comprehension and to consider our place within the grand cosmic web. By studying Laniakea, we not only uncover the secrets of the cosmos but also deepen our understanding of ourselves and our connection to the universe. The story of Laniakea continues to unravel as we delve deeper into its structure and the processes that define its existence. Within its vast expanse, we encounter not only galaxies and stars but also the intergalactic medium, a diffuse mixture of gas and particles that fills the spaces between galaxies. This medium is more than just empty space. It plays a vital role in the cosmic ecosystem, serving as both a repository for matter and a site for complex interactions. The intergalactic medium is primarily composed of hydrogen, the most abundant element in the universe, along with traces of helium and heavier elements. It is heated and enriched by the explosive deaths of stars, such as supernovae, which eject massive amounts of energy and matter into space. This process spreads elements like carbon, oxygen, and iron throughout the supercluster, creating the building blocks for new stars, planets, and potentially life itself. The intergalactic medium also acts as a conduit for the transfer of energy and matter between galaxies, facilitating the growth and evolution of these systems. One of the most fascinating aspects of Laniakea is the way galaxies within it move in a coordinated flow toward the Great Attractor. This movement is not random but is governed by the gravitational interactions between galaxies, clusters, and dark matter. By studying the velocities of galaxies and their trajectories, astronomers have constructed detailed maps of Laniakea's structure, revealing the intricate web of connections that define the supercluster. These maps have shown that Laniakea is not uniform but is composed of substructures, clusters and groups of galaxies linked by filaments of matter. These substructures, such as the Virgo cluster, serve as the building blocks of the supercluster. Each cluster contains hundreds to thousands of galaxies, bound together by their mutual gravitational attraction. Within these clusters, galaxies can collide, merge, and interact, leading to bursts of star formation and the redistribution of matter. Galaxy clusters are also home to some of the most extreme environments in the universe. The intense gravitational forces within clusters cause gas to heat up to millions of degrees, emitting X-rays that can be detected by space telescopes. This hot gas is a valuable tool for astronomers, as it provides clues about the distribution of dark matter within clusters. By analyzing the X-ray emission from galaxy clusters in Laniakea, scientists can gain insights into the properties of dark matter and its role in shaping the universe. Another intriguing phenomenon within Laniakea is the existence of galaxy mergers. When two galaxies collide, their gravitational fields interact, distorting their shapes and triggering the formation of new stars. These mergers can result in the creation of larger galaxies, often elliptical in shape, and are a key driver of galactic evolution. The Milky Way itself has undergone numerous mergers in its history and is expected to merge with Andromeda in the distant future. In addition to galaxy mergers, Laniakea is also a site of intense star formation. Within the supercluster, regions of dense gas and dust provide the raw materials for the birth of new stars. These stellar nurseries are often located in the spiral arms of galaxies, where gravitational interactions compress the gas and trigger the formation of stars. The rate of star formation varies across Laniakea, with some galaxies experiencing rapid bursts of activity, while others remain relatively quiescent. The diversity of galaxies within Laniakea is another remarkable feature. From massive elliptical galaxies to delicate spiral galaxies and irregular systems, the supercluster showcases the full spectrum of galactic forms. Each type of galaxy has its own unique characteristics and evolutionary history, shaped by factors such as its environment, interactions with neighboring galaxies, and the availability of gas for star formation. For example, spiral galaxies like the Milky Way are characterized by their prominent disk structures and spiral arms, which are sites of active star formation. In contrast, elliptical galaxies are more rounded and lack the distinct structure of spirals, often containing older stars and little gas. Irregular galaxies, as their name suggests, have no defined shape and are often the result of gravitational interactions or mergers. The study of Laniakea also sheds light on the role of black holes in shaping galaxies and their environments. Supermassive black holes, which reside at the centers of most galaxies, have a profound impact on their surroundings. These black holes can emit powerful jets of energy and particles, known as active galactic nuclei, which influence the distribution of gas and the rate of star formation within their host galaxies. By examining the activity of black holes in Laniakea, astronomers can better understand their role in the cosmic ecosystem. One of the most profound questions surrounding Laniakea is its place within the larger cosmic web. While Laniakea is a massive structure, it is not the largest in the universe. Superclusters are part of an even more extensive network of filaments and voids that span the cosmos. These structures are connected by the flow of matter and energy, forming a web-like pattern that extends across billions of light years. This cosmic web is a testament to the interconnectedness of the universe. The threads of the web are composed of dark matter and galaxies, while the voids represent regions of lower density. The interactions between these components create a dynamic and ever-changing universe, where the boundaries between structures are often blurred. By studying Laniakea within the context of the cosmic web, scientists can gain a deeper understanding of how the universe evolved from its earliest moments to its present state. The exploration of Laniakea is not just a scientific endeavor but also a journey of philosophical reflection. It challenges us to consider our place in the universe and the vastness of the cosmos. The realization that the Milky Way is just one of hundreds of thousands of galaxies within Laniakea, and that Laniakea itself is just one supercluster among many, highlights the sheer scale of the universe and our small but significant role within it. As we look to the future, the study of Laniakea promises to reveal even more about the universe's mysteries. Advances in technology, such as the development of more powerful telescopes and computational tools, will enable us to probe deeper into the structure and dynamics of the supercluster. These discoveries will not only enhance our understanding of Laniakea but also provide valuable insights into the fundamental nature of the universe. The journey to unravel the secrets of Laniakea is far from over. Each new discovery adds another piece to the puzzle, bringing us closer to a comprehensive understanding of the universe's largest structures. And yet, for every question we answer, new mysteries emerge, reminding us that the universe is as enigmatic as it is vast. The mysteries of Laniakea seem endless, drawing us into a deeper understanding of not just the structure of the universe but also the profound interconnectedness that governs it. Within the Laniakea Supercluster, the behavior of galaxies, clusters, and the filaments of dark matter create a ballet that stretches across time and space. To understand this complex dance, astronomers have turned to the most advanced tools of modern science, combining observations from telescopes, simulations, and theoretical models. One of the most groundbreaking techniques used to study Laniakea is redshift mapping. As light travels from distant galaxies to Earth, it is stretched by the expansion of the universe, a phenomenon known as redshift. By measuring the redshift of galaxies, astronomers can determine their velocities and distances, effectively creating a three-dimensional map of their positions within the supercluster. This mapping is essential for identifying the flow of galaxies and their movement toward the Great Attractor. The Great Attractor itself is a compelling and enigmatic feature of Laniakea. Situated approximately 150 million light-years away in the direction of the Centaurus constellation, it exerts a gravitational pull so immense that it affects the motion of entire clusters of galaxies. Yet, much about the Great Attractor remains hidden. It lies in the so-called zone of avoidance, an area of the sky obscured by the dense dust and gas of the Milky Way. This makes direct observation challenging, requiring astronomers to rely on indirect methods to study it. What lies at the heart of the Great Attractor? Some theories suggest it could be a massive cluster of galaxies or an exceptionally dense region of dark matter. Others propose that it is a remnant of the early universe, a relic of the primordial fluctuations that seeded the cosmic web. Whatever its true nature, the Great Attractor is a focal point in the narrative of Laniakea, a gravitational anchor that defines the movement and structure of the supercluster. As we continue to explore the dynamics of Laniakea, the role of dark matter becomes increasingly apparent. Dark matter, which does not emit, absorb, or reflect light, is an invisible but crucial component of the universe. It provides the scaffolding for galaxies and clusters, shaping their formation and evolution. Within Laniakea, dark matter forms a network of filaments that connect galaxies and clusters, creating the framework of the supercluster. Scientists have inferred the presence of dark matter through its gravitational effects on visible matter. For example, the rotation curves of galaxies, how their rotational speed varies with distance from the center, cannot be explained by the visible mass alone. Similarly, the gravitational lensing of light from distant galaxies provides evidence for the distribution of dark matter in and around clusters. By mapping the dark matter in Laniakea, astronomers can better understand how its gravity influences the movement of galaxies toward the Great Attractor. Laniakea is not just a static structure, it is constantly evolving. Over billions of years, galaxies and clusters within the supercluster will continue to move and interact, driven by the gravitational forces at play. Some galaxies may merge, forming larger systems, while others may be stripped of their gas and stars in close encounters with clusters. The filaments of dark matter that connect these structures may also shift and change, altering the flow of matter through the supercluster. The future of Laniakea is tied to the fate of the universe itself. As the universe expands, the distances between galaxies and clusters will grow, and the influence of dark energy, a mysterious force driving this expansion, will become increasingly dominant. Over trillions of years, the galaxies within Laniakea may drift apart, their light redshifted beyond visibility, leaving behind a dark and isolated cosmos. This scenario, known as the Big Freeze, is a sobering reminder of the impermanence of even the largest structures in the universe. Yet, within the context of human timescales, Laniakea remains a dynamic and vibrant system. It offers an unparalleled opportunity to study the interplay of forces that shape the cosmos, from the pull of gravity to the expansion of space. By examining the galaxies, clusters, an intergalactic medium within Laniakea, astronomers can uncover the processes that govern the formation and evolution of cosmic structures. The study of Laniakea also has implications beyond astrophysics. It touches on questions of philosophy, existentialism, and our place in the cosmos. The realization that our Milky Way is part of a vast supercluster, itself a small part of the cosmic web, invites us to reflect on the scale of the universe and our role within it. It challenges us to think about the connections between the micro and macro, the individual and the collective, and the fleeting nature of our existence against the backdrop of cosmic time. As we peer deeper into the mysteries of Laniakea, we are reminded of the boundless curiosity that drives human exploration. Each discovery, no matter how small, adds to our understanding of the universe and our place within it. And while the answers may not always be immediate or complete, the pursuit of knowledge is a journey worth undertaking, a journey that connects us to the stars, the galaxies, and the vast tapestry of the cosmos. The story of Laniakea is far from over. With each new observation and insight, we uncover another layer of this intricate and beautiful supercluster. It is a testament to the power of human ingenuity and the enduring quest to understand the universe. And as we look to the future, the mysteries of Laniakea will continue to inspire, challenge, and captivate us, reminding us of the infinite possibilities that lie beyond the stars. The vastness of the Laniakea Supercluster brings us to one of the most fascinating aspects of its study, the role of intergalactic connections. While individual galaxies are awe-inspiring in their own right, their interactions and the web-like structure they form are what give Laniakea its unique identity. Galaxies within the supercluster are not isolated entities. They are connected by filaments of gas, dark matter, and gravitational forces that create a dynamic, living system. These filaments serve as the arteries of the cosmic web, transferring matter and energy between galaxies and clusters. One of the most intriguing questions about Laniakea is how these intergalactic connections formed. The current understanding stems from the Big Bang, the event that set the universe into motion around 13.8 billion years ago. In the aftermath of the Big Bang, tiny quantum fluctuations in the density of matter were amplified by gravity, eventually leading to the formation of galaxies, clusters, and superclusters. Over time, gravity pulled matter together along these filaments, creating the intricate network we observe today. The study of these filaments is a growing field in astronomy, thanks in part to advancements in technology and observational techniques. Telescopes equipped with sensitive spectrographs can detect the faint glow of hydrogen gas within these filaments, revealing their structure and composition. Computer simulations, such as those from the Illustris or Eagle projects, provide a detailed look at how these filaments evolve over billions of years, allowing scientists to compare theoretical models with observational data. Interestingly, the filaments in Laniakea are not uniform. Some are dense and rich in galaxies, while others are more sparse, resembling cosmic highways that guide matter toward clusters. These differences are influenced by the distribution of dark matter, which acts as the gravitational backbone of the supercluster. Where dark matter is more concentrated, the filaments are thicker and more pronounced, while regions with less dark matter are thinner and less structured. The movement of galaxies along these filaments is another area of active research. Galaxies are not stationary. They are constantly in motion, pulled by the combined gravitational forces of nearby structures. Within Laniakea, this movement is directed toward the Great Attractor, creating a phenomenon known as bulk flow. This flow is not random but follows the contours of the supercluster, illustrating the interconnectedness of its components. Studying this movement provides valuable insights into the distribution of mass within Laniakea, including the elusive dark matter. By tracking the velocities of galaxies, astronomers can infer the gravitational influence of unseen mass, creating a more complete picture of the supercluster's structure. This approach has already revealed surprising details, such as the presence of previously unknown substructures and the complex interactions between clusters. One of the most compelling mysteries of Laniakea is the role of dark energy. While gravity pulls galaxies together, dark energy drives the universe's expansion, pushing galaxies apart. This cosmic tug-of-war shapes the evolution of superclusters like Laniakea. Over time, the influence of dark energy is expected to grow, causing galaxies to drift further apart and weakening the gravitational bonds that hold them together. What does this mean for Laniakea? In the distant future, the supercluster may lose its cohesion, with galaxies becoming isolated islands in an ever-expanding universe. This scenario, often referred to as cosmic isolation, highlights the transient nature of even the most massive structures in the cosmos. Yet, in the present epoch, Laniakea remains a vibrant and interconnected system, offering a window into the forces that shape the universe. The interconnectedness of Laniakea also has implications for the study of galactic evolution. Galaxies within the supercluster are influenced by their environment, including interactions with other galaxies and the intergalactic medium. These interactions can trigger star formation, strip away gas, or even lead to galactic mergers, creating a dynamic and ever-changing landscape. One fascinating example is the phenomenon of ram pressure stripping, which occurs when a galaxy moves through the dense gas of a cluster. The pressure from this interaction can strip away the galaxy's gas, halting star formation and transforming its appearance. This process is a key driver of galactic evolution within Laniakea, shaping the diversity of galaxies we observe today. Mergers, too, play a significant role in the life of galaxies within Laniakea. When two galaxies collide, their stars, gas, and dark matter interact in complex ways, leading to the formation of new stars and the growth of supermassive black holes at their centers. These events are not rare. In fact, the Milky Way itself is on a collision course with the Andromeda Galaxy, a member of the Local Group, which is part of the Laniakea Supercluster. This future merger will reshape our galactic neighborhood, creating a new, larger galaxy over billions of years. The study of these interactions is made possible by powerful telescopes and simulations. Observatories like the Hubble Space Telescope and the Atacama Large Millimeter/Submillimeter Array, ALMA, provide detailed images of merging galaxies and their aftermath, while simulations offer a glimpse into the future of such events. Together, these tools paint a vivid picture of the dynamic processes at work within Laniakea. Despite the progress made in understanding Laniakea, many questions remain unanswered. What is the true nature of the Great Attractor? How does dark matter shape the supercluster's structure? What role does dark energy play in its evolution? These mysteries are a reminder of the vastness of the universe and the limits of our knowledge. Yet, they also serve as a source of inspiration, driving scientists to push the boundaries of discovery. As we continue to explore Laniakea, we are not just uncovering the secrets of a distant supercluster, we are also gaining a deeper appreciation for our place in the cosmos. The interconnected web of galaxies, the flow of matter, and the forces that shape the universe all point to a profound truth, that we are part of something much larger than ourselves. This realization is both humbling and exhilarating, a testament to the beauty and complexity of the universe. The journey to understand Laniakea is far from over. With each new discovery, we take another step closer to unraveling the mysteries of our galactic neighborhood. And as we look to the future, the promise of new technologies and insights ensures that the story of Laniakea will continue to unfold, captivating and inspiring generations to come. The unfolding story of the Laniakea Supercluster reveals much about the delicate balance between the forces that govern the cosmos. As we delve deeper into its complexities, one critical aspect emerges: the role of gravity in shaping its structure and dynamics. Gravity is not just a force that holds stars within galaxies. It is the architect of the vast cosmic web, orchestrating the motion of galaxies and clusters within the intricate framework of Laniakea. Understanding how gravity functions on these immense scales requires the study of peculiar velocities, the motion of galaxies that deviates from the general expansion of the universe. These peculiar velocities are influenced by the gravitational pull of nearby structures, including massive galaxy clusters and superclusters. In Laniakea, the peculiar velocities of galaxies provide a detailed map of the gravitational forces at play, highlighting regions of high density and revealing the flow of matter toward the Great Attractor. The Great Attractor itself remains one of the most enigmatic features of Laniakea. Situated approximately 150 million light-years away from Earth, This massive region exerts a gravitational pull so strong that it influences the motion of entire galaxies across vast distances. Despite its immense influence, the exact nature of the Great Attractor is shrouded in mystery. Observations suggest it is a dense concentration of galaxies, gas, and dark matter, but its precise composition and structure are still under investigation. Adding to the intrigue is the fact that the Great Attractor lies within the zone of avoidance, a region of the sky obscured by the Milky Way's dense disk. The dust and gas of our galaxy make it challenging to observe this region in visible light, forcing astronomers to rely on alternative methods such as infrared and X-ray observations. These techniques have provided glimpses of the Great Attractor, but a complete picture remains elusive, leaving scientists eager to uncover its secrets. Another fascinating feature of Laniakea is the concept of gravitational binding. While the supercluster is vast and contains countless galaxies, not all of its components are gravitationally bound to one another. Over time, the expansion of the universe driven by dark energy will weaken the gravitational connections between distant parts of Laniakea. This process will eventually isolate individual clusters and galaxies, transforming the supercluster into a collection of disconnected islands in an ever-expanding cosmos. This future scenario raises profound questions about the nature of cosmic structures and their longevity. Superclusters like Laniakea are not permanent fixtures in the universe. They are dynamic entities shaped by the interplay of gravity and expansion. Studying their evolution provides a unique opportunity to understand the life cycle of cosmic structures, from their formation to their eventual dispersal. The role of dark matter in this process cannot be overstated. Dark matter, an invisible and enigmatic substance, makes up the majority of the mass in Laniakea. It is the scaffolding upon which the supercluster is built, providing the gravitational framework that holds its components together. Without dark matter, the intricate web of galaxies and filaments that define Laniakea would not exist. Yet, despite its significance, dark matter remains one of the greatest mysteries in astrophysics. Its exact nature and composition are unknown, and its interactions with ordinary matter are limited to gravitational effects. Efforts to detect dark matter directly have so far been unsuccessful, but ongoing experiments and observations continue to push the boundaries of our understanding. The presence of dark matter also has implications for the distribution of galaxies within Laniakea. Galaxies tend to cluster around regions of high dark matter density, creating a pattern that mirrors the underlying dark matter structure. This alignment is not random but follows the principles of cosmic evolution, where gravity amplifies initial density fluctuations to form the large-scale structures we see today. The study of these structures is made possible by advanced simulations that model the universe's evolution. These simulations incorporate the effects of gravity, dark matter, and dark energy, providing a virtual laboratory to test theories and predict outcomes. In the case of Laniakea, simulations have revealed the complex interplay between its components, offering insights into the forces that shape its structure and dynamics. One of the most compelling aspects of Laniakea is its place within the broader cosmic web. While it is a massive and intricate structure, it is not isolated. It is part of a larger network of superclusters connected by filaments and voids. These connections create a hierarchy of structures, with Laniakea serving as one node in the vast tapestry of the universe. The relationships between superclusters are governed by the same forces that shape their internal dynamics. Gravity pulls them together, while dark energy drives them apart. This duality creates a delicate balance, resulting in the intricate patterns observed in the cosmic web. By studying Laniakea in the context of its surroundings, scientists can gain a deeper understanding of the universe's large-scale structure and the forces that govern it. The exploration of Laniakea also has implications for understanding the origins of galaxies and their evolution. The conditions within the supercluster, including its density, temperature, and composition, influence the formation and behavior of galaxies. For example, galaxies in dense regions of Laniakea are more likely to experience interactions and mergers, leading to the formation of larger, more complex systems. These interactions are not limited to individual galaxies. They also occur between clusters and groups within Laniakea. When clusters collide, Their hot gas and dark matter interact in ways that provide valuable insights into the nature of these components. Observations of such collisions, such as the famous bullet cluster, have been instrumental in studying dark matter and its behavior. Despite the progress made in understanding Laniakea, many mysteries remain. What is the ultimate fate of the supercluster? How will its structure evolve over billions of years? What role does dark energy play in shaping its future? These questions drive ongoing research, highlighting the dynamic and ever-changing nature of the cosmos. The study of Laniakea is not just a scientific endeavor, it is also a profound exploration of our place in the universe. The realization that our galaxy is part of such an immense and interconnected structure is both humbling and inspiring. It reminds us of the vastness of the cosmos and the intricate web of relationships that define it. As we continue to unravel the mysteries of Laniakea, we are not just learning about a distant supercluster, we are uncovering the story of the universe itself. Each discovery adds a new chapter to this story, enriching our understanding of the cosmos and our place within it. And as the journey of exploration continues, the promise of new insights and revelations ensures that the study of Laniakea will remain a source of wonder and inspiration for generations to come. The future of the Laniakea Supercluster offers a glimpse into the broader fate of the universe. As we observe the interactions and dynamics within this supercluster, it becomes evident that Laniakea is a microcosm of the cosmic forces that govern all structures in the universe. To understand its eventual destiny, we must consider the influence of dark energy and the accelerating expansion of the cosmos. Dark energy, a mysterious force driving the accelerated expansion of the universe, plays a critical role in determining the future of superclusters like Laniakea. Over time, dark energy is expected to weaken the gravitational bonds holding galaxies and clusters together, gradually isolating individual systems. This process, often referred to as the cosmic isolation effect, means that galaxies within Laniakea that are not gravitationally bound to one another will drift apart as the universe continues to expand. The eventual separation of galaxies will transform Laniakea into a fragmented network of clusters and voids. While gravitationally bound systems such as galaxy groups and clusters will remain intact, the larger-scale structure of the supercluster will become increasingly diffuse. This scenario highlights the delicate interplay between gravity and dark energy, emphasizing how these competing forces shape the evolution of cosmic structures. One of the most profound questions about Laniakea's future involves the role of dark matter in sustaining its structure. Dark matter, which accounts for the majority of the supercluster's mass, is the invisible backbone of Laniakea. Its gravitational influence binds galaxies together, creating the intricate web of filaments and nodes that define the supercluster. However, as dark energy becomes increasingly dominant, the ability of dark matter to maintain these connections will diminish. The study of dark matter in the context of Laniakea is crucial for understanding its properties and behavior. Observations of galaxy motions and cluster dynamics provide indirect evidence of dark matter's presence, but its exact nature remains elusive. Is it composed of exotic particles, such as weakly interacting massive particles, WIMPs, or does it represent a modification of our understanding of gravity? These questions drive ongoing research and experimentation, with Laniakea serving as a natural laboratory for exploring the mysteries of dark matter. The Great Attractor, a central feature of Laniakea, also holds clues to the supercluster's long-term evolution. As a dense region of mass concentration, the Great Attractor exerts a powerful gravitational pull on surrounding galaxies and clusters. Its influence extends across vast distances, shaping the flow of matter within Laniakea. However, the ultimate fate of the Great Attractor itself remains uncertain. Will it continue to grow by accreting more galaxies, or will it eventually succumb to the isolating effects of dark energy? Understanding the Great Attractor requires detailed observations of its environment and composition. The zone of avoidance, which obscures much of this region from view, presents a significant challenge to astronomers. Nevertheless, advances in technology and observational techniques, such as infrared and X-ray imaging, are gradually revealing the hidden features of the Great Attractor. These efforts are shedding light on its role within Laniakea and its relationship to the broader cosmic web. Another intriguing aspect of Laniakea's future involves the potential for galaxy interactions and mergers. As galaxies within the supercluster move along their respective paths, some will inevitably collide and merge, forming larger and more complex systems. These interactions are not random but are influenced by the gravitational landscape of Laniakea. Dense regions, such as the cores of clusters, are hotspots for galaxy mergers, where the forces of gravity bring galaxies into close proximity. Galaxy mergers play a crucial role in shaping the evolution of galaxies, driving star formation and altering their morphology. When two galaxies merge, their gas clouds collide and compress, triggering bursts of star formation. Over time, the combined system settles into a new equilibrium, often taking on an elliptical shape. These processes contribute to the diversity of galaxy types observed within Laniakea, from spirals to ellipticals and irregulars. Despite the apparent chaos of galaxy mergers, these events also provide opportunities for studying the underlying physics of the universe. Observations of merging galaxies allow astronomers to probe the behavior of dark matter, as well as the interplay between gas, stars, and black holes. By examining the remnants of past mergers, scientists can reconstruct the history of interactions within Laniakea, piecing together the story of its formation and evolution. The cosmic voids surrounding Laniakea are equally important for understanding its structure and dynamics. These vast, empty regions represent areas where matter is relatively scarce, in stark contrast to the dense filaments and clusters of the supercluster. Voids are not completely empty but contain low-density gas, dark matter, and faint galaxies. Their presence influences the motion of galaxies within Laniakea, as gravitational forces act to pull matter away from voids and toward denser regions. The study of voids offers a unique perspective on the universe's large-scale structure. These regions provide a counterpoint to the dense nodes and filaments of the cosmic web, highlighting the balance between overdense and underdense areas. Observations of voids also contribute to our understanding of dark energy, as their expansion rates provide valuable constraints on the properties of this mysterious force. Looking further ahead, the ultimate fate of Laniakea is intertwined with the fate of the universe itself. If the expansion of the universe continues to accelerate, as current observations suggest, the supercluster will become increasingly fragmented over time. Galaxies and clusters will drift apart, leaving behind isolated islands of matter in a vast and empty cosmos. This scenario, known as the heat death of the universe, represents a future where the large-scale structure of the cosmos dissolves into a state of maximum entropy. While this vision of the future may seem bleak, it also underscores the importance of studying cosmic structures like Laniakea. By understanding the forces that shape and govern the universe, we gain insight into the fundamental nature of reality. Laniakea serves as a testament to the interconnectedness of the cosmos, reminding us of the intricate web of relationships that bind galaxies, clusters, and superclusters together. As we continue to explore the mysteries of Laniakea, we are not just uncovering the secrets of a distant supercluster, we are expanding our understanding of the universe and our place within it. The story of Laniakea is a story of discovery, one that inspires wonder and curiosity about the vast and complex cosmos we call home. And as new technologies and observations push the boundaries of our knowledge, the journey of exploration promises to reveal even more about this extraordinary galactic neighborhood. Laniakea's position within the grander cosmic tapestry provides us with a unique vantage point to explore how superclusters form, evolve, and interact over billions of years. While Laniakea is the supercluster that contains our Milky Way galaxy, it is far from being an isolated, self-contained region. Instead, it exists within a vast, interconnected web of superclusters that span enormous distances across the observable universe. This web, known as the cosmic web, is a structure formed by gravitational forces over the course of billions of years. The cosmic web is not just a theoretical model, it is a tangible, observable phenomenon, and Laniakea plays a significant role in this structure. When we look beyond Laniakea, we see the existence of other superclusters, massive collections of galaxies that, like Laniakea, are bound together by gravity. These superclusters form part of an even larger structure called the Laniakea Wall, which is a region in the universe marked by dense clusters of galaxies and superclusters. This wall extends over vast distances and gives the impression of a nearly uninterrupted cosmic structure that spans billions of light years. Within this grand structure, Laniakea is just one of many superclusters, each with its own distinct gravitational influence on the galaxies it contains. As we look at the universe from the vantage point of Laniakea, the cosmic web becomes clearer, with filaments of galaxies and clusters connected by vast voids. These filaments are not uniform, and their shape and density are influenced by the initial conditions of the universe. The formation of these structures traces back to the Big Bang, and their evolution is shaped by the forces of gravity, dark matter, and dark energy. Understanding the role of Laniakea within this larger structure provides a clearer picture of how the universe as a whole has evolved over time. The interplay between galaxies, superclusters, and the cosmic web is an ongoing process, driven by both the expansion of the universe and the gravitational forces that pull galaxies and clusters together. This balance between expansion and attraction determines the movement of galaxies within superclusters like Laniakea. While the expansion of the universe is accelerating due to dark energy, gravity continues to exert its pull, keeping galaxies in clusters and preventing them from flying apart. Over time, however, the balance may shift. If dark energy continues to dominate, galaxies within Laniakea may begin to drift away from each other, leading to a more isolated and diffuse supercluster in the distant future. One of the most fascinating aspects of Laniakea is its potential to teach us about the early universe. By studying the motion and distribution of galaxies within the supercluster, astronomers can infer crucial details about the conditions that existed shortly after the Big Bang. The structure of Laniakea is a relic of the early universe, shaped by the gravitational collapse of matter and the expansion of space. The way galaxies are distributed within the supercluster provides insights into the forces that shape the cosmic structure and the distribution of dark matter. The fact that Laniakea has such a large number of galaxies in motion also offers a wealth of data that can be used to study the physics of galaxy formation and evolution. Galaxies within Laniakea are not static. They are constantly moving and interacting with each other. As mentioned earlier, these interactions can result in galaxy mergers, which in turn drive the evolution of the galaxies themselves. Studying these processes within the context of a large, interconnected supercluster like Laniakea gives astronomers the opportunity to observe galaxy formation in real time, providing valuable information about the forces that govern the behavior of galaxies on large scales. In addition to the study of galaxy interactions, Laniakea's vast expanse also provides a valuable laboratory for understanding the distribution of dark matter. Dark matter, which is invisible and detectable only through its gravitational influence, makes up a significant portion of the mass within the supercluster. By examining how galaxies within Laniakea move and interact, scientists can better understand the distribution of dark matter and its role in shaping the structure of the supercluster. The study of dark matter is one of the most exciting frontiers in modern astrophysics, and Laniakea, with its vast collection of galaxies, provides an ideal setting for this research. Another fascinating aspect of Laniakea's role within the cosmic web is its connection to the Great Attractor. The Great Attractor is a massive concentration of galaxies and dark matter located at the center of Laniakea, and it exerts a strong gravitational pull on the galaxies within the supercluster. This region is of particular interest because it is responsible for the peculiar motion of galaxies within Laniakea. The Great Attractor's gravity is so powerful that it affects the motion of galaxies over vast distances, influencing their trajectories and velocities. The exact nature of the Great Attractor remains one of the great mysteries of modern astrophysics, as its precise location and structure are still being studied. As our understanding of Laniakea deepens, scientists are increasingly able to map the distribution of mass within the supercluster, including both visible matter, such as stars and galaxies, and dark matter. This mapping is essential for understanding how Laniakea and other superclusters fit into the broader structure of the universe. The study of superclusters is critical for understanding the formation of galaxies and the large-scale structure of the cosmos. Without a complete understanding of these structures, it would be difficult to grasp the overall history and future of the universe. Beyond the physical processes that shape Laniakea, the study of this supercluster raises important philosophical questions about the nature of our existence in the cosmos. The realization that the Milky Way is just one of countless galaxies within a vast supercluster, itself part of an even larger structure, forces us to reconsider our place in the universe. It challenges us to think about the nature of life, the scale of the universe, and the forces that govern the cosmos. If our galaxy is part of such a massive and intricate structure, what does that say about the potential for life elsewhere in the universe? Could other intelligent civilizations exist within the vast expanse of the cosmic web, or are we alone in our corner of the universe? These questions also highlight the importance of continued exploration and discovery. As our understanding of Laniakea and other superclusters expands, we are likely to uncover new insights into the fundamental nature of the universe. The mysteries of the cosmos are far from being fully understood, and each new discovery brings us closer to answering some of the most profound questions about the universe's origins, its current state, and its eventual fate. The Laniakea Supercluster, as part of the larger cosmic web, serves as a reminder of the vastness of the universe and the complexity of the forces that shape it. It represents a nexus of galaxies, stars, and dark matter, interconnected by gravity and the fabric of spacetime itself. Studying Laniakea provides a glimpse into the cosmic processes that have shaped the universe over billions of years, and it offers a window into the future of the universe as it continues to expand and evolve. The story of Laniakea is far from over, and as our understanding of the cosmos deepens, so too will our appreciation for the intricacies of this extraordinary galactic neighborhood. Laniakea's role in the cosmic web stretches far beyond its immediate boundaries, shaping the motion of galaxies over vast distances. The gravitational influence of superclusters like Laniakea affects the movement of galaxies on an unimaginable scale. Galaxies within Laniakea are drawn toward the region of highest density, known as the Great Attractor, and are in a constant state of motion as they respond to the complex gravitational forces of the supercluster. The Great Attractor, which is a major point of interest in Laniakea, has been one of the most enigmatic objects in astrophysics for decades. Although scientists are still working to pinpoint its exact structure and makeup, its gravitational pull has been well documented. The galaxies in the Laniakea Supercluster, including our own Milky Way, are moving toward the Great Attractor at a rate of millions of miles per hour. This motion provides vital clues about how matter is distributed in the universe, offering astronomers insight into the unseen forces that control the cosmic structure. One of the key aspects that makes Laniakea so fascinating is the fact that it provides us with a glimpse of the underlying forces at work within the universe. The supercluster's boundaries and the movement of its constituent galaxies are influenced by factors such as dark matter, dark energy, and the expansion of the universe itself. Dark matter, which makes up a significant portion of the mass in Laniakea, is still largely a mystery to scientists. Its presence is inferred through its gravitational effects, yet its composition remains one of the biggest unsolved puzzles in cosmology. The behavior of dark matter within superclusters like Laniakea is a subject of great interest. It is thought that dark matter plays a crucial role in the formation of galaxies and large-scale structures. Because it interacts with regular matter only through gravity and possibly weak forces, it is invisible to most observational techniques. However, its gravitational influence is undeniable, and it is likely that dark matter is what holds galaxies and clusters of galaxies together, preventing them from flying apart despite the expansion of the universe. The precise nature of dark matter and its role in the structure of superclusters is a central area of research in modern astrophysics. In addition to dark matter, dark energy is another mysterious force that shapes the universe on a grand scale. Dark energy, which is thought to make up roughly 68% of the total energy content of the universe, is responsible for the accelerated expansion of space. This mysterious force acts as a counterbalance to gravity, pushing galaxies apart rather than pulling them together. The interplay between dark matter and dark energy has profound implications for the evolution of superclusters like Laniakea. As the universe continues to expand, the balance between these forces will determine the future of superclusters and the fate of the universe itself. The sheer size of Laniakea, encompassing roughly 100,000 galaxies over 500 million light-years, offers a unique opportunity for studying the large-scale structure of the universe. By analyzing the distribution of galaxies within the supercluster, scientists can gain insights into the way matter has been organized since the early universe. The motion of galaxies within Laniakea, along with their interactions and clustering patterns, tells us about the processes that have shaped the universe since the Big Bang. What makes Laniakea even more intriguing is the fact that its study provides a rare opportunity to understand the past and future of our own galaxy, the Milky Way. As one of the many galaxies within this supercluster, our galaxy is not an isolated entity. It is part of a much larger system that is constantly evolving and interacting with other galaxies. The motion of the Milky Way within Laniakea is influenced by both local and distant forces, and the interactions between galaxies within the supercluster will eventually shape the Milky Way's future. Astronomers have long known that galaxies are not evenly distributed throughout the universe. Instead, they tend to cluster together in large groups, forming structures like superclusters. The formation of these structures is driven by the gravitational attraction of matter, and Laniakea is a prime example of how such structures come together. The complex dynamics of galaxy clustering within Laniakea offer valuable clues about the processes that govern galaxy formation and evolution. The distribution of galaxies within the supercluster is not random. Rather, it follows a pattern influenced by the underlying forces of gravity, dark matter, and dark energy. Galaxies within Laniakea tend to be concentrated in clusters and filaments, with large voids separating them. These voids are not empty. They are regions with very few galaxies, and their existence is a direct result of the way gravity has shaped the universe over billions of years. The galaxies in Laniakea are connected by vast cosmic filaments of dark matter and gas, creating a vast web of matter that spans the supercluster and beyond. As we look even further out, the study of Laniakea gives us a glimpse into the broader structure of the universe. Superclusters like Laniakea are not isolated. They are part of a vast cosmic web that stretches across the observable universe. This web consists of galaxies, superclusters, and vast voids, all interconnected by the forces of gravity and dark matter. The cosmic web is one of the largest structures in the universe, and understanding it is essential for understanding how the universe has evolved over time. The study of Laniakea and its place within the cosmic web also provides important insights into the future of the universe. As the universe continues to expand, the distances between galaxies are growing larger. The accelerated expansion of the universe, driven by dark energy, is causing galaxies to move away from one another at an ever-increasing rate. Over time, this expansion will cause the galaxies in Laniakea to move further apart, eventually leading to a scenario where the supercluster becomes more diffuse and isolated. While this process will take billions of years, it raises intriguing questions about the long-term fate of superclusters and the ultimate destiny of the universe. One of the most exciting prospects of studying superclusters like Laniakea is the potential for discovering new phenomena and mysteries that could reshape our understanding of the cosmos. As observational techniques continue to improve, astronomers will be able to peer even deeper into the heart of Laniakea and other superclusters. This could lead to the discovery of new types of galaxies, exotic cosmic objects, or even unknown forces that shape the structure of the universe. The study of Laniakea is still in its early stages, and there is much more to learn about this vast and complex region of the cosmos. As we continue to explore the mysteries of Laniakea and the larger cosmic web, we are reminded of the profound scale of the universe and our place within it. Our galaxy, the Milky Way, is just one small part of an enormous supercluster, itself part of an even greater cosmic structure. The universe is vast, and our understanding of it is still incomplete. Yet, each new discovery brings us closer to unraveling the mysteries of the cosmos, offering new insights into the fundamental nature of reality and our place within it. The Laniakea Supercluster is not just an astronomical object, it is a symbol of the interconnectedness of the universe. It serves as a reminder that everything in the cosmos, from the smallest particles to the largest structures, is bound together by the forces of gravity and the fundamental laws of physics. The study of Laniakea is a journey into the heart of the universe, a journey that will continue to unfold for generations to come. As we uncover the secrets of this vast supercluster and its place within the cosmic web, we gain a deeper understanding of the universe and our place within it, a place that is both humbling and awe-inspiring. As we delve further into the intricate structure of the Laniakea Supercluster, it's important to note that the supercluster itself is not just an isolated region within the universe. It exists within a much larger context of interconnected superclusters, which together form a network that spans across vast distances. This network, often referred to as the cosmic web, is the largest known structure in the universe, and understanding Laniakea's place within this web offers valuable insights into the broader forces at play in the cosmos. The cosmic web consists of filaments of galaxies, dark matter, and gas, stretching across billions of light-years of space. These filaments connect superclusters like Laniakea, forming a vast interconnected network that binds the universe together on the largest scales. At the intersections of these filaments, galaxy clusters and superclusters are often found, while the voids between them remain largely empty. These voids are not truly empty, however. They are filled with a diffuse, nearly invisible substance, dark energy, that drives the accelerated expansion of the universe. What makes the study of Laniakea so significant is that it serves as a microcosm of the cosmic web. By understanding the dynamics of Laniakea and the forces that shape it, astronomers can gain a deeper understanding of how larger cosmic structures evolve and interact. The Laniakea Supercluster, like all superclusters, is shaped by the gravitational pull of dark matter and the expansive force of dark energy. These two forces, though largely invisible and poorly understood, are the primary drivers behind the formation and evolution of galaxies, clusters, and superclusters. In addition to the study of dark matter and dark energy, Laniakea's position within the cosmic web provides valuable insights into the history of the universe itself. The arrangement of galaxies within the supercluster is a direct result of the distribution of matter and energy that existed in the early universe. By mapping the positions and motions of galaxies within Laniakea, astronomers can trace the growth of the universe from its earliest moments to its current state, offering clues about the processes that led to the formation of galaxies, stars, and planets. The motion of galaxies within the Laniakea Supercluster is another key area of study. As mentioned earlier, the galaxies within Laniakea are not stationary. They are constantly moving toward the Great Attractor, a mysterious region of space that exerts a gravitational pull on the galaxies within the supercluster. This motion is not random. It is influenced by the gravitational forces exerted by other galaxies, as well as the distribution of dark matter throughout the supercluster. The galaxies in Laniakea are bound together by these forces, creating a dynamic and ever-changing cosmic structure. One of the most intriguing aspects of Laniakea's motion is its connection to the larger-scale movement of the universe. The expansion of the universe itself is one of the most significant discoveries of modern cosmology, and understanding how superclusters like Laniakea fit into this expanding universe is crucial for understanding the future of the cosmos. The galaxies in Laniakea, like all galaxies, are moving away from each other as the universe continues to expand. However, the gravitational pull of the Great Attractor and other nearby superclusters is causing galaxies in Laniakea to move toward one another, creating a tug-of-war between the expansion of the universe and the gravitational forces within superclusters. This tension between the expansion of the universe and the gravitational forces within superclusters has profound implications for the future of the universe. If the expansion of the universe continues to accelerate, as current observations suggest, the galaxies in Laniakea and other superclusters may eventually be pushed apart, leading to a more diffuse universe. On the other hand, if the gravitational pull of superclusters becomes strong enough, it could eventually counteract the expansion of the universe, leading to a big crunch, in which the universe contracts and collapses in on itself. The study of Laniakea and its place within the larger universe also offers valuable insights into the potential for future discoveries. As our observational techniques continue to improve, scientists are developing new methods for studying distant galaxies, dark matter, and dark energy. With the advent of more powerful telescopes and space-based observatories, astronomers will be able to probe deeper into the heart of Laniakea and other superclusters, uncovering new phenomena and refining our understanding of the universe's structure and evolution. One area of particular interest is the study of galaxy mergers within superclusters like Laniakea. Galaxies are not static objects, they are in a constant state of interaction, colliding and merging with one another over cosmic timescales. These galaxy mergers play a crucial role in the evolution of galaxies, often leading to the formation of new stars, the development of supermassive black holes, and changes in the overall structure of galaxies. The collisions between galaxies and Laniakea are thought to be a significant driver of the supercluster's evolution, shaping its future and influencing the motion of galaxies within it. The impact of these galaxy mergers extends beyond Laniakea itself. When galaxies collide, they release vast amounts of energy, including radiation and gravitational waves, which can have far-reaching effects on their surroundings. These events provide valuable clues about the nature of the universe and the forces that govern it. By studying the effects of galaxy mergers within Laniakea, scientists can gain a better understanding of the processes that shape galaxies and their interactions, offering insights into the future of the universe. As we continue to explore the mysteries of Laniakea, it becomes clear that the supercluster is a vital piece of the cosmic puzzle. Its size, motion, and structure provide valuable clues about the forces that shape the universe and the underlying processes that govern the formation and evolution of galaxies. The study of Laniakea is not just a study of a single supercluster, it is a study of the universe itself, a journey into the heart of the cosmos that will continue to unfold for generations to come. Laniakea serves as a reminder of the vastness and complexity of the universe. While it may seem like just one supercluster among many, its study offers insights into the nature of space, time, and gravity, as well as the forces that shape the universe's evolution. As we continue to study Laniakea, we are not only uncovering the secrets of a distant supercluster, but also gaining a deeper understanding of the cosmos as a whole. As we continue our exploration of Laniakea, it's essential to discuss the broader implications that this supercluster has for our understanding of the universe. When we look up at the stars at night, we are often struck by the sheer number of individual stars we can see, but we fail to grasp the enormity of the universe as a whole. The scale of the universe is so vast that it challenges our perception of space and time. Within this overwhelming scale, Laniakea stands as one of the many building blocks of the cosmic structure. At the heart of Laniakea lies the Great Attractor, a mysterious anomaly that has puzzled scientists since it was first identified in the 1970s. The Great Attractor is a region of space where galaxies, including those in Laniakea, appear to be moving toward, drawn by an unseen force. While the exact nature of the Great Attractor remains unclear, its influence on the galaxies within Laniakea is undeniable. The force exerted by the Great Attractor seems to be an intense gravitational pull that affects the entire supercluster, causing galaxies to move toward it at significant speeds. This region is located about 150 million light-years from Earth, and though it is situated within the Laniakea supercluster, its exact nature remains a subject of intense study. What makes the Great Attractor particularly intriguing is the fact that it is largely obscured from our view. The area around it is filled with dense intergalactic gas, which blocks our ability to observe the region directly. As a result, astronomers are left to deduce the characteristics of the Great Attractor by observing the motion of galaxies around it. The gravitational pull of the Great Attractor is so strong that it is affecting the entire motion of our galaxy, the Milky Way, as well as other galaxies in Laniakea. However, the Great Attractor is not the only fascinating aspect of Laniakea's gravitational dynamics. One of the most important contributions of this supercluster to our understanding of the universe is the study of galactic flows. Galactic flows are the large-scale movements of galaxies across the universe, influenced by the gravitational interactions between galaxies, dark matter, and the unseen forces of dark energy. These flows are not random. Rather, they are influenced by the distribution of matter across the universe. The concept of galactic flows was largely developed in the 1980s when astronomers began to notice that galaxies in certain regions of space were not moving in a way that matched the expected expansion of the universe. Instead, these galaxies were moving toward each other, suggesting that there was some kind of gravitational pull at play. The study of galactic flows has since become an essential part of cosmology, providing insight into the distribution of mass and energy on the largest scales. Laniakea, as a massive supercluster, plays a crucial role in these galactic flows, as it is both a participant and a driver of the larger movements of galaxies in the universe. Beyond the gravitational interactions between galaxies, Laniakea also contributes to our understanding of galaxy evolution. Galaxies are not static objects, they evolve over time, undergoing processes such as mergers, accretion, and star formation. The interaction of galaxies within Laniakea has led to the formation of numerous galaxy clusters, each of which is a highly dynamic region where galaxies are interacting and evolving. These interactions, over billions of years, contribute to the growth and evolution of the galaxies that inhabit the supercluster. In addition to the traditional processes of galaxy evolution, Laniakea also provides a unique opportunity to study the role of dark matter in shaping galaxies. Dark matter, which makes up about 27% of the universe's mass, is an invisible substance that interacts with regular matter only through gravity. It cannot be seen directly, but its presence can be inferred by its gravitational effects. Within superclusters like Laniakea, dark matter plays a critical role in shaping the structure of galaxies and galaxy clusters. The gravitational pull of dark matter is thought to be responsible for holding galaxies together, preventing them from flying apart due to their internal motion. Without dark matter, galaxies like the Milky Way would likely not exist in their current form. As our observational capabilities improve, we are learning more about the intricate ways in which dark matter interacts with regular matter. Advanced technologies, such as the James Webb Space Telescope, are allowing astronomers to peer deeper into the universe and investigate the role of dark matter in superclusters like Laniakea. The study of dark matter remains one of the most important and challenging areas of modern astrophysics, and Laniakea serves as a natural laboratory for understanding its effects on a cosmic scale. But it's not just the matter we can see that shapes Laniakea and the larger universe. It's also the invisible forces that govern the cosmos. One of the most enigmatic of these forces is dark energy. Dark energy is a mysterious form of energy that is believed to be responsible for the accelerated expansion of the universe. It is thought to make up about 68% of the universe's energy content, yet it remains largely undetectable by current instruments. The presence of dark energy is inferred from its effects on the large-scale structure of the universe, such as the accelerated motion of galaxies and the expansion of space itself. In superclusters like Laniakea, dark energy plays a significant role in shaping the long-term evolution of the cosmos. While gravitational forces work to pull galaxies and clusters together, dark energy works in the opposite direction, pushing galaxies apart. This tug-of-war between gravity and dark energy is one of the key factors that will determine the future of the universe. If dark energy continues to dominate, the universe will continue expanding at an accelerated rate, eventually leading to the Big Freeze, where galaxies are separated by vast distances and the cosmos becomes an increasingly cold and empty place. The study of Laniakea is helping us understand how these invisible forces, dark matter and dark energy, shape the evolution of galaxies and superclusters. While these forces are still poorly understood, their effects are evident throughout the universe. The more we learn about the way these forces interact with visible matter, the more we can begin to understand the ultimate fate of the universe itself. Laniakea's position within the cosmic web also allows for the study of how superclusters interact with one another on the largest scales. While galaxies and clusters within a supercluster are bound together by gravity, the boundaries between superclusters are much less defined. Superclusters like Laniakea are not isolated islands in the universe. They are connected to other superclusters through vast cosmic filaments, forming a network that stretches across the observable universe. These filaments are thought to be composed of dark matter and gas, and they provide the pathways through which superclusters interact and influence one another. Understanding the interactions between superclusters is crucial for understanding the structure of the universe as a whole. Superclusters do not exist in isolation. They are part of a larger web that connects them to other regions of space. By studying how superclusters like Laniakea interact with their neighbors, scientists can learn more about the fundamental forces that govern the universe, as well as the role that superclusters play in shaping the cosmic web. In the future, as our understanding of dark matter, dark energy, and galactic motion deepens, the study of superclusters like Laniakea will continue to offer profound insights into the nature of the universe. The discoveries made in the Laniakea Supercluster may lead to a greater understanding of the forces that govern the cosmos, the origins of galaxies and stars, and the future of the universe itself. As we push the boundaries of our knowledge, we must acknowledge that Laniakea is not just a supercluster of galaxies. It serves as a living, breathing snapshot of cosmic processes that have been ongoing for billions of years. The study of Laniakea offers us a glimpse into the formation, evolution, and ultimate fate of the universe. Each galaxy within it tells a story, and each interaction between these galaxies reveals something fundamental about how the universe works. One particularly fascinating aspect of Laniakea is how it's helping to reveal the mysteries of galaxy formation and cluster dynamics. It has long been known that galaxies evolve over time, but understanding the exact mechanisms behind their evolution is much more difficult. Galaxies can grow through the accumulation of matter, both gas and dark matter, and through mergers with other galaxies. In Laniakea, we are fortunate to observe many examples of these processes happening right before our eyes. The interactions between galaxies in the supercluster serve as a cosmic laboratory, showing us the ways in which galaxies collide, merge, and evolve. Over millions to billions of years, these mergers can result in the formation of larger galaxies or even entire galaxy clusters, like the one we call the Laniakea Supercluster. Galaxy mergers are a key component of this process. These mergers occur when two or more galaxies collide and then interact gravitationally. As a result, their structures can change dramatically. The individual stars and stellar systems within the galaxies may not directly collide due to the vast distances between them, but the gravitational forces can distort the galaxy's shapes, stir up star formation, and create new structures such as tidal tails or rings. The Milky Way, our home galaxy, is on a collision course with the Andromeda Galaxy, one of the other major members of the Laniakea Supercluster. This will likely result in the formation of a new galaxy, often referred to as Milkomeda or Milkomeda. But galaxy mergers are not just important because of their spectacular, transformative nature. They provide valuable insight into the distribution of dark matter in the universe. As galaxies interact, their dark matter halos, large regions of dark matter that surround galaxies, also interact. These interactions can reveal information about the way dark matter behaves, which remains one of the greatest mysteries in modern physics. The study of galaxy mergers within Laniakea offers astronomers the opportunity to examine the relationship between visible matter, such as stars and gas, and the invisible matter that makes up most of the mass in the universe. Moreover, these galactic interactions within Laniakea provide us with the opportunity to better understand the role of supermassive black holes. Supermassive black holes, which are found at the centers of most large galaxies, play an important role in shaping the dynamics of their host galaxies. When galaxies merge, their central black holes can eventually collide and combine, creating even more massive black holes. These interactions have a profound effect on the galaxies they inhabit, influencing star formation, galaxy structure, and the release of energy in the form of radiation and jets of particles. The study of these interactions, especially within the context of Laniakea, is helping astronomers understand how these mysterious objects affect the evolution of galaxies and superclusters. As Laniakea continues to be a source of research, one of the most important findings that astronomers hope to achieve is uncovering the large-scale structure of the universe in greater detail. The discovery of the Laniakea Supercluster marked a major milestone in our understanding of the universe's organization. Prior to this discovery, we knew that galaxies were distributed throughout the universe, but we lacked a clear picture of how these galaxies were grouped together. The identification of superclusters like Laniakea has revealed that galaxies are not distributed randomly, but instead form vast cosmic structures that can be traced across the universe. These structures help to reveal the large-scale distribution of dark matter and dark energy, which are thought to make up the majority of the universe's mass and energy. By mapping out the locations of superclusters like Laniakea, astronomers are piecing together a map of the universe on the largest scales, which will ultimately help us understand its origins, evolution, and future. The cosmic web, which connects superclusters like Laniakea, is another fascinating feature of the universe that has been revealed through these studies. The cosmic web is a vast, filamentary structure made up of galaxy clusters, superclusters, and dark matter. These filaments stretch across the universe, forming an interconnected network of cosmic structures. Within this web, galaxies are not scattered randomly, but instead follow a clear pattern, with most galaxies located along the filaments, and large voids between the filaments. Laniakea is part of this cosmic web, and its position and interactions within this web will ultimately reveal more about the forces that shape the universe on the largest scales. The study of the cosmic web, including superclusters like Laniakea, is helping scientists investigate some of the most fundamental questions about the nature of the universe. How did the universe form? What is the role of dark matter and dark energy? How do large-scale structures evolve? These are the questions that researchers are attempting to answer as they study Laniakea and other superclusters. Each new discovery brings us one step closer to understanding the origins of the universe and our place within it. Looking to the future, the study of Laniakea is poised to continue shaping our understanding of the cosmos. With the advent of new technologies, including the James Webb Space Telescope and next-generation radio telescopes, astronomers will be able to probe deeper into the universe than ever before. These tools will allow researchers to study distant galaxies and clusters within Laniakea, uncovering new details about their structure, composition, and behavior. As our observational capabilities improve, we may discover new, previously unknown aspects of the supercluster, such as hidden dark matter structures, mysterious cosmic phenomena, or even new insights into the formation of galaxies. One particularly exciting area of research is the potential discovery of new, more distant superclusters that are connected to Laniakea. While Laniakea is currently one of the largest known superclusters, it is possible that there are even larger structures yet to be discovered. As we continue to explore the depths of the universe, new superclusters may be found, offering us an even more detailed picture of the universe's structure. These discoveries would challenge our current understanding of the cosmic web and could reveal new insights into the nature of dark matter, dark energy, and the expansion of the universe. In addition to technological advancements, future theoretical research will continue to play a crucial role in our understanding of Laniakea and the universe as a whole. New models of cosmic evolution, based on the latest observational data, will help us refine our understanding of how superclusters like Laniakea form and evolve. These models will also help us better understand the role of superclusters in the larger dynamics of the universe, such as the cosmic expansion, galaxy formation, and the growth of large-scale structures. As we continue to push the boundaries of our knowledge, Laniakea will remain a key player in our understanding of the universe. Its immense scale, intricate gravitational interactions, and connections to the larger cosmic web make it a natural focus for astronomers and cosmologists. Through the study of Laniakea and other superclusters, we will continue to uncover the secrets of the universe and unlock the mysteries of the cosmos. The mysteries of Laniakea extend far beyond its role as a supercluster of galaxies. It is a bridge that connects us to the deepest, most fundamental questions of the universe. As we explore the supercluster's vast expanse, we begin to grasp how the entire universe is interwoven in a web of cosmic forces. The Milky Way's place within this massive structure is not just a fact about our neighborhood in the cosmos. It is an entry point into understanding the larger structure of the universe itself. Laniakea serves as a key player in understanding the concept of cosmic flow, the movement of galaxies and their clusters across vast distances. The way galaxies within Laniakea move is influenced by the gravitational pull exerted by other galaxies and clusters, including the mass of the supercluster itself. This is part of a larger phenomenon known as the cosmic flow, where galaxies appear to move toward larger gravitational structures like superclusters. At the heart of this cosmic flow is the Great Attractor, a mysterious, unseen force located in the direction of the Hydra Centaurus supercluster. It is thought to be the point of convergence for a vast number of galaxies within the Laniakea Supercluster, pulling them toward it. However, what exactly the Great Attractor is remains one of the most tantalizing mysteries in astrophysics. It is believed to be an area of extremely high mass concentration, but it is largely invisible to current telescopes due to the thick layers of galactic dust between us and it. What we know is that the Great Attractor's gravitational pull is so strong that it affects galaxies even from hundreds of millions of light-years away. Laniakea's galaxies are all moving toward it, suggesting that the Great Attractor may be the focal point of a massive structure, perhaps even a supercluster. However, the exact nature of this region remains a subject of intense speculation and ongoing research. It is a place that seems to defy our understanding, offering yet another piece of the cosmic puzzle that astronomers and physicists are working to solve. The discovery of Laniakea also sparked a deeper discussion about the overall large-scale structure of the universe. For much of modern history, scientists viewed the universe as a seemingly random scattering of galaxies, without much order or interconnectedness. However, the realization that galaxies are organized into superclusters and larger structures, like Laniakea, has forced us to reconsider the universe's structure. The web-like formation of these superclusters suggests that the universe is not a random scatter of stars and galaxies, but rather a highly organized system governed by the laws of physics. This interconnectedness also suggests that the universe's structure may be much more predictable than we once thought. One of the greatest challenges in modern cosmology is understanding the role of dark matter in these large-scale structures. Dark matter, the invisible substance that does not emit or interact with electromagnetic radiation, is believed to make up about 85% of the matter in the universe. It is thought to exert a gravitational influence on galaxies and superclusters, shaping the way they move and evolve over time. In Laniakea, dark matter plays a crucial role in holding the entire supercluster together. While we cannot directly observe dark matter, its presence is inferred from the gravitational effects it exerts on visible matter. The study of dark matter in Laniakea is helping scientists develop new models of how galaxies and clusters interact, offering insights into the structure and behavior of the universe as a whole. As we peer deeper into Laniakea, we also begin to understand how these cosmic forces shape the life cycles of galaxies. The supercluster is not a static structure, it is dynamic, constantly changing, evolving, and reshaping itself. Over billions of years, the galaxies within Laniakea will continue to merge, form new stars, and eventually evolve into new and different structures. This process, known as galaxy evolution, is at the heart of what makes Laniakea so fascinating. Each galaxy within it has a story to tell about the birth, life, and death of cosmic objects. It is through the study of these galaxies that we can gain insights into how the universe itself is evolving. Laniakea also provides us with a unique opportunity to study the history of the universe. By observing galaxies at different stages in their evolution, we can look back in time and understand how the universe has changed over billions of years. This process is called cosmology, and it involves studying the large-scale structure of the universe to reconstruct its history. The Milky Way, as a member of Laniakea, is no exception. It has undergone significant changes over the billions of years since it formed, evolving from a smaller, more compact galaxy into the spiral galaxy we see today. The study of Laniakea offers astronomers a rare opportunity to study the Milky Way's past, present, and future in the context of the larger universe. Another important aspect of Laniakea's study is its role in helping us understand the nature of cosmic acceleration. The expansion of the universe is one of the most fundamental aspects of cosmology. Since the Big Bang, the universe has been expanding, with galaxies moving away from each other as the fabric of space-time stretches. However, in recent decades, astronomers have discovered that this expansion is not slowing down, as previously thought. Instead, the expansion of the universe is accelerating, driven by a mysterious force known as dark energy. This discovery has revolutionized our understanding of the universe and raised new questions about the nature of space-time. The study of Laniakea is crucial in this context, as it may help provide clues about how cosmic acceleration works on the largest scales. The motion of galaxies within the supercluster, particularly their movement toward the Great Attractor, may offer insights into the role of dark energy in the expansion of the universe. As we continue to study Laniakea, we also gain a better understanding of the cosmic forces that govern the behavior of galaxies, superclusters, and the universe as a whole. The interconnectedness of these vast cosmic structures is a testament to the underlying unity of the universe. In the vastness of space, everything is connected. The Milky Way, the Andromeda Galaxy, and countless other galaxies are all part of the same cosmic neighborhood. They are bound together by the same fundamental forces, and together they form the largest and most complex structures in the universe. The story of Laniakea is the story of the universe itself. It is a story of creation, evolution, and the endless pursuit of knowledge. As we continue to probe deeper into the mysteries of the cosmos, Laniakea will remain at the forefront of our efforts. It will continue to reveal new insights into the nature of dark matter, dark energy, and the large-scale structure of the universe. It will continue to inspire new questions and spark new discoveries. And perhaps most importantly, it will remind us of the vastness and complexity of the universe, a universe that is still full of secrets waiting to be uncovered. Through the study of Laniakea, we are not just learning about a distant supercluster. We are learning about the very fabric of reality itself. We are learning about the forces that shape the cosmos, the interactions between galaxies, and the way the universe is evolving. And, as we continue to explore the farthest reaches of space, we may one day find ourselves standing at the threshold of the greatest discoveries the universe has to offer. As we peer further into the depths of the Laniakea Supercluster, it becomes clear that this region of space is more than just a collection of galaxies. It is a tapestry of cosmic activity, each galaxy, star, and nebula contributing to a larger, dynamic system. The gravitational forces that bind the galaxies together form intricate patterns, much like threads in a vast cosmic web. This structure extends far beyond Laniakea, as we begin to realize that the universe itself is composed of superclusters, clusters, and vast voids, all interconnected in a way that stretches the limits of our understanding. One of the most fascinating aspects of Laniakea's composition is the intricate dance of its constituent galaxies. Each galaxy, from the massive elliptical ones to the smaller irregular galaxies, is constantly moving. The Milky Way, for instance, is not stationary. It is on a journey, heading toward the Andromeda Galaxy in a grand cosmic collision that will take place in about 4.5 billion years. This collision, known as the Milkomeda event, will reshape both galaxies, merging them into a new, larger galaxy. In the context of Laniakea, this movement is just a tiny part of the larger cosmic ballet in which all galaxies participate. This ongoing motion within the supercluster reveals just how dynamic our universe is, constantly evolving and transforming over incomprehensible spans of time. The cosmic flow that defines Laniakea does not just affect galaxies, it influences the very fabric of space-time. The movement of galaxies, along with the gravitational interactions between them, causes ripples in space-time. These ripples, known as gravitational waves, are a fundamental prediction of Einstein's theory of general relativity. In recent years, scientists have detected these ripples coming from distant parts of the universe, providing direct evidence of the dynamic, ever-changing nature of space-time. The study of gravitational waves has opened up new avenues of exploration, allowing us to observe the universe in ways previously thought impossible. By examining the gravitational waves emitted by distant events, scientists can gain insights into the most extreme environments in the universe, such as black holes and neutron stars, as well as the overall structure of superclusters like Laniakea. At the heart of Laniakea, we find the Great Attractor, a force of nature that continues to baffle scientists. Located about 150 million light-years from Earth, the Great Attractor is thought to be a vast concentration of mass, possibly a supermassive black hole or a group of dense galaxy clusters, whose gravitational pull affects the movement of galaxies across an enormous region of space. The exact nature of the Great Attractor is still uncertain, largely because it lies behind the dense plane of the Milky Way galaxy, making it difficult to observe directly. However, its influence is undeniable. The galaxies within Laniakea are all drawn toward it, and as we study the way these galaxies move, we learn more about the forces that shape the universe on the grandest scales. In addition to the Great Attractor, another intriguing feature of Laniakea is the role of dark matter. As mentioned earlier, dark matter is an invisible substance that exerts a gravitational pull on visible matter, but does not interact with light or other forms of electromagnetic radiation. This makes it undetectable through conventional telescopes, but scientists have inferred its presence by observing its effects on the movement of galaxies. Dark matter is believed to make up the majority of the mass in the universe, and its influence can be seen throughout Laniakea. The gravitational forces exerted by dark matter are what keep the galaxies within the supercluster bound together. Without dark matter, the galaxies would not move in the patterns we observe today. The study of dark matter is still in its infancy, but understanding its role in Laniakea is a crucial step in unlocking the mysteries of the universe. The study of Laniakea has also raised important questions about the nature of the universe itself. For decades, scientists have debated whether the universe is infinite or finite. The discovery of superclusters like Laniakea suggests that the universe is not just infinite, but also incredibly organized. The large-scale structure of the universe, with its clusters and superclusters, points to a higher level of order that is yet to be fully understood. If the universe is organized into a vast cosmic web, with galaxies and clusters connected by gravitational forces, what does that say about the fundamental nature of space and time? Are we living in a universe that is fundamentally predictable, governed by the laws of physics, or is there an element of chaos that we have yet to comprehend? These questions are at the heart of modern cosmology, and the answers may lie within the structure of Laniakea. Another aspect of Laniakea that has captivated scientists is its potential to hold the key to understanding the future of the universe. The motion of galaxies within the supercluster is not random. It follows predictable patterns based on the gravitational forces at play. This means that, over time, the structure of Laniakea will continue to evolve. Galaxies will continue to move toward the Great Attractor, and in the distant future, some of them may merge, forming new and larger galaxies. This process is not unique to Laniakea. It is happening throughout the universe. The study of Laniakea, with its vast array of galaxies and complex gravitational interactions, provides us with a glimpse into the future of the universe. By understanding how galaxies evolve within superclusters, we can begin to predict how the universe will continue to change over billions of years. One of the most profound implications of studying superclusters like Laniakea is the realization that we are not just observing the universe, we are part of it. The Milky Way, our home galaxy, is just one of billions in the Laniakea Supercluster, and our existence is intertwined with the vast cosmic forces that shape it. We are connected to the rest of the universe in ways that we are only beginning to understand. The study of Laniakea reminds us that we are not isolated in space, but rather part of a much larger, interconnected system. It is a humbling realization that challenges our understanding of our place in the cosmos. As we continue to explore the mysteries of Laniakea, we are faced with questions that may never have definitive answers. What is the nature of the Great Attractor? How does dark matter shape the movement of galaxies? What will become of the Milky Way in the distant future? These are questions that may take centuries, if not longer, to answer. But as we delve deeper into the heart of Laniakea, we are reminded that the pursuit of knowledge is an ongoing journey, one that will continue to unfold as we explore the vastness of the cosmos. The mysteries of Laniakea are not just about understanding a distant supercluster. They are about understanding the very nature of the universe itself. The story of Laniakea is the story of discovery. It is a story of how human curiosity has driven us to explore the farthest reaches of space, seeking answers to questions that have haunted us for millennia. It is a story of how, through perseverance and ingenuity, we have uncovered the hidden structures of the universe, from the smallest galaxies to the largest superclusters. And it is a story of how, in the process, we have come to realize that the universe is far more mysterious and awe-inspiring than we could have ever imagined. As we continue to explore the vastness of space, the mysteries of Laniakea will remain at the forefront of our quest for knowledge, guiding us toward a deeper understanding of the cosmos and our place within it. The journey into the Laniakea Supercluster is not merely a study of galaxies, stars, or nebulae, it's an exploration of the very fabric that binds the cosmos together. As we continue to probe deeper into the vastness of this colossal region, we come to understand that Laniakea is a microcosm of the universe itself, representing both the complexity and elegance of cosmic evolution. The galaxy clusters and cosmic structures within Laniakea are not isolated. They are interconnected by a delicate web of forces, stretching across the universe in ways that are still being deciphered. One of the most awe-inspiring features of Laniakea is the vast network of galaxy filaments and voids that stretch far beyond our immediate neighborhood. While Laniakea itself may appear to be a single, cohesive supercluster, it is, in reality, part of a much larger, evolving cosmic tapestry. The galaxies within Laniakea are not just bound together by gravity. They are part of a much grander structure of cosmic filaments, long, thread-like formations of galaxies that are the largest structures in the universe. These filaments form a vast cosmic web, with voids or empty regions between them. Understanding the role of these filaments and voids in the larger structure of the universe is key to understanding how Laniakea fits into the grand cosmic order. This cosmic web is the result of billions of years of evolution, driven by the fundamental forces of the universe. The gravitational forces that bind galaxies within superclusters like Laniakea are not static. They are ever-changing, influenced by the continuous motion of galaxies, dark matter, and the expansion of the universe itself. This expansion is a fundamental feature of our universe, and it plays a crucial role in shaping the large-scale structure of the cosmos. Since the Big Bang, the universe has been expanding, with galaxies moving away from each other over time. This expansion is not uniform, however. Certain regions, such as superclusters, are growing at different rates due to the influence of dark energy and the gravitational pull of nearby structures. Laniakea, like other superclusters, is not immune to the forces of this cosmic expansion. As the universe continues to expand, the galaxies within Laniakea are moving apart at an accelerating rate. However, the gravitational forces that bind Laniakea together are strong enough to counteract this expansion on smaller scales, keeping the galaxies within the supercluster in relative proximity to one another. This balance between expansion and gravitational attraction is a key feature of the universe's structure, and has significant implications for the future of Laniakea and other superclusters. As we consider the future of Laniakea, it is impossible to ignore the larger question of the ultimate fate of the universe itself. The ongoing expansion of the universe, the motion of galaxies, and the complex interplay of forces within superclusters like Laniakea are all part of a much larger cosmic puzzle. Scientists are still debating how this puzzle will ultimately play out. Some theories suggest that the universe will continue to expand indefinitely, with galaxies drifting further apart over time. Others propose the possibility of a Big Crunch, in which the expansion of the universe eventually slows and reverses, causing galaxies to collapse back into a singularity. Still, others speculate about more exotic possibilities, such as the Big Rip, in which the acceleration of the universe's expansion becomes so extreme that it tears apart galaxies, stars, and even atoms themselves. While these theories may seem speculative, they reflect the profound mysteries that remain at the heart of our understanding of the cosmos. The future of Laniakea, and of the universe itself, is deeply intertwined with these fundamental questions. As we continue to explore the nature of superclusters, dark matter, dark energy, and the forces that shape our universe, we may uncover answers that challenge our very notions of time, space, and existence. In the meantime, the study of Laniakea provides us with an extraordinary opportunity to examine the large-scale structure of the universe. By observing the motion of galaxies within the supercluster, scientists can learn about the gravitational interactions that govern the cosmos, as well as the role of dark matter and dark energy in shaping the universe's evolution. These observations have profound implications for our understanding of the fundamental laws of physics, and they may help us answer some of the most profound questions about the nature of reality itself. One of the most exciting developments in the study of Laniakea and the universe at large is the advent of new technologies and observational techniques. In recent years, advancements in radio astronomy, gravitational wave detection, and space-based telescopes have opened up new avenues for exploring the cosmos. These technologies allow scientists to probe regions of space that were previously inaccessible, providing a wealth of new data that can help us better understand the structure and evolution of the universe. For example, the upcoming James Webb Space Telescope, set to launch in the near future, promises to revolutionize our understanding of the universe. With its unprecedented resolution and sensitivity, the Webb telescope will be able to observe galaxies, stars, and other cosmic objects in greater detail than ever before. This will allow scientists to study the structure of Laniakea and other superclusters with a level of precision that was previously unimaginable. As we begin to gather more data about the distant reaches of the universe, we will be able to refine our models of galaxy formation, dark matter, and the expansion of the cosmos. In addition to technological advancements, the study of Laniakea and other superclusters is also benefiting from new theoretical models and simulations. Using powerful supercomputers, scientists can create detailed simulations of the large-scale structure of the universe, modeling the behavior of galaxies, dark matter, and other cosmic components over billions of years. These simulations help researchers test their theories about the evolution of superclusters and the broader cosmic web, allowing them to make predictions about the future of Laniakea and other similar regions. These advancements in technology and theory are pushing the boundaries of our understanding of the universe and our place within it. As we continue to explore Laniakea and other superclusters, we are constantly reminded of the vastness and complexity of the cosmos. The more we learn about the universe, the more we realize how little we truly know. But that is the beauty of science. The constant pursuit of knowledge, the relentless drive to uncover the mysteries of the cosmos, and the endless fascination with the unknown. Ultimately, the story of Laniakea is a story of exploration, discovery, and wonder. It is a story that continues to unfold, revealing new insights into the nature of the universe and our place within it. As we look toward the future, we can only imagine what new revelations will come to light. Perhaps, in the years to come, we will unlock even greater secrets about the supercluster that contains our Milky Way, the forces that shape its motion, and the ultimate fate of the universe itself. Laniakea is a reminder that, despite how much we have learned about the cosmos, there is always more to discover. It challenges our perceptions of space and time, and forces us to confront the humbling reality that we are just a small part of a much larger, more intricate universe. In the end, it is the mysteries of Laniakea, and the universe beyond, that continue to inspire us, driving us to push the boundaries of human knowledge and explore the vast, uncharted reaches of space. As we delve further into the Laniakea Supercluster, it becomes evident that our place in the universe is both humbling and extraordinary. The supercluster is not simply an isolated collection of galaxies. It's a dynamic, evolving system that is deeply connected to the rest of the cosmos. The movement of galaxies within Laniakea, as well as their interaction with other neighboring superclusters, creates a cosmic ballet that is constantly changing, with each galaxy playing a vital role in the grand structure of the universe. One fascinating aspect of Laniakea is how its structure impacts our understanding of the universe's history. By studying the motion of galaxies within this supercluster, scientists can trace the origins of Laniakea and even the universe itself. In essence, the galaxies within Laniakea serve as cosmic time capsules, preserving clues about the universe's past. Each galaxy carries within it a story, a record of the conditions that existed when it formed, and a testament to the forces that have shaped its development over billions of years. Understanding the formation of Laniakea requires a deep dive into the history of galaxy formation. Galaxies are not static objects. They are born, grow, and evolve over time. The earliest galaxies formed shortly after the Big Bang, when the universe was a hot, dense place. As the universe expanded and cooled, matter began to clump together, eventually forming stars and galaxies. The gravitational attraction between these galaxies led to the formation of larger structures, such as galaxy clusters and superclusters. Laniakea's formation is the result of these gravitational interactions. The galaxies within the supercluster are drawn together by gravity, forming a massive web-like structure. This process of galaxy formation and clustering has been ongoing for billions of years, and it continues to this day. While Laniakea may appear to be a stable, well-defined structure, it is, in fact, still evolving. New galaxies are constantly being formed, while others are being pulled into the supercluster from neighboring regions. The motion of galaxies within Laniakea is a key factor in understanding its structure and evolution. Galaxies within the supercluster are not moving randomly, they are part of a larger cosmic flow. This flow is driven by the gravitational pull of Laniakea's central regions, where the largest and most massive galaxies reside. These galaxies act as gravitational anchors, pulling smaller galaxies toward them and shaping the motion of the entire supercluster. This flow of galaxies is not just limited to Laniakea, it is a feature of the universe as a whole. The motion of galaxies is influenced by the large-scale structure of the cosmos, which is composed of a vast network of filaments and voids. These filaments, which are made up of galaxies, dark matter, and gas, connect superclusters like Laniakea and create a web-like structure that spans the entire universe. This web is not a static feature, it is constantly changing, with galaxies moving along these filaments and being drawn toward the gravitational centers of superclusters. In this cosmic web, Laniakea is just one of many superclusters. Each supercluster is connected to others through vast cosmic filaments, creating a complex, interconnected structure. This web of superclusters and filaments is a crucial feature of the universe's large-scale structure, and understanding it is key to understanding the overall evolution of the cosmos. While Laniakea is one of the largest superclusters in the known universe, it is not unique. There are other superclusters scattered throughout the cosmos, each with its own unique features and structure. Some, like Laniakea, are relatively isolated, while others are part of even larger structures. These superclusters are all interconnected, forming a vast, intricate cosmic network that spans the entire universe. Despite its vast size and complexity, Laniakea is not immune to the same fundamental forces that govern the rest of the universe. The supercluster is constantly being shaped by the expansion of the universe, as well as the gravitational pull of nearby structures. This expansion is a key factor in the future of Laniakea and the larger universe as a whole. As the universe continues to expand, galaxies within Laniakea will continue to move further apart. However, the gravitational forces that bind the supercluster together will keep it from completely dispersing. In the distant future, the fate of Laniakea will depend on a number of factors, including the expansion rate of the universe, the distribution of dark energy, and the gravitational pull of other superclusters. It is possible that Laniakea will remain a stable structure for billions of years, but it is also possible that it will eventually be drawn into the gravitational pull of a neighboring supercluster, leading to a dramatic merger. The potential for such mergers and interactions is one of the most exciting aspects of studying superclusters like Laniakea. These cosmic collisions can have profound effects on the galaxies within the superclusters, leading to the formation of new stars, the destruction of old ones, and the reshaping of the cosmic landscape. The study of these interactions is one of the most exciting areas of research in modern cosmology, and it holds the key to understanding the future of Laniakea and the universe as a whole. One of the most significant discoveries in recent years has been the realization that the universe is not just expanding, it is accelerating. This discovery, which was made possible by observations of distant supernovae, has revolutionized our understanding of the cosmos. The expansion of the universe is being driven by a mysterious force known as dark energy, which makes up a large portion of the universe's total energy content. Dark energy is thought to be responsible for the accelerated expansion of the universe, and its effects are felt throughout the cosmos, including within superclusters like Laniakea. The influence of dark energy on Laniakea is still not fully understood, but it is clear that this mysterious force is playing a key role in the future evolution of the supercluster. As the universe continues to expand, the influence of dark energy will become even more pronounced. This could lead to a dramatic acceleration in the motion of galaxies within Laniakea, causing them to move apart at an even faster rate. The eventual outcome of this accelerated expansion is still uncertain, but it is likely that it will have a significant impact on the future of the supercluster. The study of Laniakea and other superclusters is also shedding light on the role of dark matter in the universe's large-scale structure. Dark matter, which makes up a significant portion of the universe's total mass, is thought to be responsible for the formation of galaxy clusters and superclusters. It is believed that dark matter acts as a gravitational anchor, helping to hold galaxies together and influence their motion. While dark matter itself is invisible and cannot be directly observed, its effects on the motion of galaxies and the formation of cosmic structures can be detected through careful observations. As we continue to study Laniakea and other superclusters, we are constantly learning more about the role of dark matter and dark energy in shaping the universe. These discoveries are helping us to build a more complete picture of the cosmos and our place within it. While there is still much we do not know about the universe, the study of Laniakea is providing us with valuable insights into the fundamental forces that govern the cosmos and the future of the universe itself. The mysteries of Laniakea and the cosmic web continue to captivate the imagination of scientists and astronomers around the world. As we look deeper into the vast expanse of the universe, we are reminded of how little we truly know. Every discovery brings with it new questions, new mysteries, and new opportunities for exploration. The future of cosmology is filled with possibilities, and the study of superclusters like Laniakea will undoubtedly play a central role in unlocking the secrets of the universe. Laniakea is not just a collection of galaxies, it is a reminder of the vastness and interconnectedness of the universe. It is a symbol of the endless journey of discovery that lies ahead, as we continue to explore the mysteries of the cosmos and uncover the secrets that have been hidden for billions of years. The story of Laniakea is a story of exploration, wonder, and curiosity, and it is a story that is far from over. The scale of Laniakea, when measured against the rest of the observable universe, invites awe and reflection. It serves as a reminder of how vast the cosmos truly is. The Milky Way, our home galaxy, is a part of this immense supercluster, yet Laniakea is only a fragment in the greater tapestry of the universe. To truly grasp the enormity of the Laniakea Supercluster, one must also understand the concept of cosmic structures that extend far beyond our immediate galactic neighborhood. Laniakea spans roughly 520 million light-years, encompassing thousands of galaxies, and is one of the largest structures in the known universe. The scale of this supercluster is mind-boggling. It's far beyond what our human minds can intuitively comprehend. Each galaxy within this supercluster moves in a unique way, influenced by the powerful gravitational forces exerted by other galaxies and the vast cosmic web that binds them. In other words, Laniakea is a dynamic, living structure. Every galaxy, including our own Milky Way, is caught in the gravitational embrace of this enormous cosmic structure, like marbles in a web of cosmic strings. One of the most significant features of Laniakea is the sheer number of galaxies it contains. Though it is only one supercluster, it hosts thousands of galaxies, many of which we may never be able to study in detail. The interactions between these galaxies are influenced by a combination of factors, including dark matter, gravitational forces, and the expansion of the universe itself. These complex interactions cause galaxies to move in intricate patterns across the vast cosmic landscape. Understanding these patterns and the forces that shape them could help us better comprehend the behavior of galaxies on a large scale. In addition to its size and complexity, Laniakea also provides a fascinating glimpse into the deeper mechanics of the universe. It shows how galaxies are not isolated but rather part of a much larger, interconnected cosmic network. The flow of galaxies within the supercluster, driven by gravitational forces and the expansion of the universe, is a process that shapes the cosmic evolution of galaxies, clusters, and superclusters. As galaxies move toward or away from each other, they influence one another in profound ways, affecting their star formation, their growth, and their eventual fate. The motion of galaxies within Laniakea is not random, but rather part of a larger cosmic dance that spans the universe. The gravitational pull of Laniakea's central regions, particularly the dense cluster at its core, causes the surrounding galaxies to move toward it. This process, called the Great Attractor, is a mysterious force that has fascinated astronomers for decades. It's a massive concentration of matter that pulls galaxies toward it, affecting the movement of galaxies across a vast expanse. This pull, however, is not entirely understood. While the Great Attractor has been identified as a massive concentration of galaxies and dark matter, its exact nature and how it influences the movement of the galaxies in Laniakea are still under investigation. The study of Laniakea has also revealed the complex web of interconnected superclusters that exist beyond it. These superclusters are not isolated entities but are part of an intricate network that stretches across the universe. This network of superclusters, often referred to as the cosmic web, consists of vast filaments of galaxies connected by dark matter. These filaments are the largest known structures in the universe, stretching across billions of light years. The cosmic web is constantly evolving, with galaxies moving along these filaments and interacting with each other in a never-ending dance. But the story doesn't end there. Laniakea's position within the cosmic web raises some profound questions about the fate of our universe. If galaxies are constantly moving along these filaments, will they eventually collide and merge? Will entire superclusters eventually come together to form even larger structures? What will the future of the universe look like as these cosmic forces continue to evolve? These questions are still open for exploration, and the answers may hold the key to understanding the ultimate fate of the universe itself. The study of Laniakea is also part of a broader effort to understand the role of dark energy in shaping the universe. Dark energy, the mysterious force that is accelerating the expansion of the universe, plays a significant role in the behavior of superclusters like Laniakea. As the universe expands, dark energy is driving galaxies apart, pushing them away from each other and increasing the rate of expansion. This process is having a profound impact on the future of superclusters like Laniakea, as they will eventually become increasingly distant from each other, leading to the gradual disintegration of the cosmic web. At the same time, the study of Laniakea also helps us understand how dark matter contributes to the formation and evolution of superclusters. Dark matter, which makes up about 27% of the universe's mass, exerts a gravitational pull that helps to shape the structure of the cosmos. While dark matter itself cannot be seen or directly measured, its presence is inferred through its gravitational effects on visible matter. Within Laniakea, dark matter acts as a kind of cosmic glue, binding galaxies together and influencing their motion across the supercluster. This interplay between dark matter and dark energy raises some fascinating questions about the future of Laniakea. Will the gravitational pull of dark matter eventually overcome the effects of dark energy? Or will dark energy continue to accelerate the expansion of the universe, pulling galaxies apart and leaving superclusters like Laniakea to drift further away from each other? These questions are still the subject of intense research and exploration, as scientists work to unravel the mysteries of these invisible forces that shape the universe. The discoveries we've made about Laniakea and its interconnectedness with the rest of the universe have profound implications for our understanding of the cosmos. The more we learn about the large-scale structure of the universe, the more we realize how much we still don't know. Every discovery leads to more questions, opening up new avenues for exploration. For example, the question of how superclusters like Laniakea are distributed throughout the universe is still an open one. Are there other superclusters out there that we have yet to discover? Are there regions of the universe that are completely devoid of galaxies? These are just some of the many questions that still remain unanswered. As our technological capabilities improve, we are gaining the ability to peer further into the cosmos than ever before. With more powerful telescopes and more advanced observational techniques, we are uncovering new details about the universe that were once beyond our reach. As we continue to study superclusters like Laniakea, we are gaining valuable insights into the processes that govern the evolution of galaxies, the large-scale structure of the universe, and the fundamental forces that shape the cosmos. One of the most exciting aspects of studying superclusters like Laniakea is the potential for future discoveries. As we continue to gather data and refine our understanding of the universe, we may uncover entirely new phenomena that challenge our current understanding of physics. For example, what if we discover that the gravitational pull of superclusters is not the only force at play? Could there be other, unknown forces in the universe that are influencing the motion of galaxies and the structure of the cosmos? The mysteries of Laniakea and the cosmic web are far from solved. But as we continue to push the boundaries of knowledge and explore the vast expanse of space, we are slowly piecing together the puzzle of the universe. Every discovery brings us closer to understanding the grand cosmic story, and the study of Laniakea will undoubtedly play a central role in that journey. Laniakea is more than just a collection of galaxies. It is a window into the vast, interconnected web of the universe. It's a reminder that our place in the cosmos is not isolated, but part of a much larger and ever-evolving structure. As we look up at the night sky, we are reminded of the incredible complexity of the universe and the mysteries that still await us. The story of Laniakea is a story of discovery, wonder, and the unyielding quest to understand the cosmos, and it is a story that will continue to unfold for generations to come. The exploration of the Laniakea Supercluster is not just about understanding the present state of the universe, but also about looking into the distant past and the potential future of our cosmic neighborhood. Through advanced telescopes, we are able to look back in time, observing distant galaxies as they were billions of years ago. The light that reaches us from these far-off galaxies carries with it crucial information about the history of the universe, allowing scientists to piece together the events that have shaped the structure of Laniakea and beyond. One of the most fascinating aspects of Laniakea's history is the idea that superclusters like it evolve over vast stretches of time. In the early universe, galaxies were more spread out and formed in smaller clusters. Over time, gravity has brought these galaxies together into larger, denser structures. This process of galaxy merging, driven by gravity and dark matter, has been happening for billions of years and will continue for billions more. As galaxies within Laniakea interact and collide, they will continue to evolve, changing in ways that we can only begin to imagine. For example, the Milky Way itself is on a collision course with the Andromeda Galaxy, which lies just outside Laniakea. While this may sound catastrophic, in reality, these galactic mergers are part of the natural cosmic cycle. When galaxies collide, they don't necessarily destroy each other. Rather, their stars pass by one another, and the galaxies may merge into a new, larger galaxy. This process, known as galactic cannibalism, has shaped the structure of galaxies throughout the universe. And in the distant future, it will also reshape the structure of Laniakea as the galaxies within it continue to interact. While the large-scale structure of Laniakea and the motion of galaxies within it are well studied, there is still much to learn about the supercluster's inner workings. For example, the role of dark matter in shaping the supercluster's structure is still not fully understood. Dark matter, which makes up roughly 27% of the universe's mass, does not emit light or energy, making it invisible to traditional observation methods. Yet, scientists can detect its presence through its gravitational effects on visible matter. In Laniakea, dark matter acts as the invisible scaffolding that holds galaxies together. It exerts a gravitational pull on visible galaxies, influencing their movement and interactions. In addition to dark matter, dark energy also plays a crucial role in the evolution of Laniakea. Dark energy, which accounts for about 68% of the universe's energy content, is responsible for the accelerated expansion of the universe. While dark matter holds galaxies together, dark energy is pushing them apart. The interplay between these two mysterious forces will determine the future of superclusters like Laniakea. As dark energy continues to accelerate the expansion of the universe, it will cause galaxies to move farther apart, potentially leading to the eventual dissipation of superclusters. The future of Laniakea and the rest of the universe is a subject of great interest to cosmologists and physicists. Will the expansion of the universe continue indefinitely, causing galaxies to drift further apart until they are no longer gravitationally bound to one another? Or will the universe eventually slow down and collapse in on itself in a big crunch? These questions remain unanswered, and the fate of superclusters like Laniakea may ultimately depend on the behavior of dark energy and dark matter. Another intriguing possibility is the idea of a Big Rip, a scenario in which the expansion of the universe accelerates to the point where even the fundamental forces of nature are overcome. In this scenario, galaxies, stars, planets, and even atoms would be torn apart as the universe expands at an ever-increasing rate. While this may sound like science fiction, it is a theoretical possibility that arises from current models of dark energy. If the expansion of the universe continues to accelerate at a faster rate, the very fabric of space-time could eventually be torn apart. However, regardless of the eventual fate of Laniakea and the universe as a whole, the study of this supercluster provides us with valuable insights into the nature of the cosmos. It serves as a reminder that our universe is not a static, unchanging place, but a dynamic and evolving system. The galaxies within Laniakea, and the supercluster itself, are all part of a larger cosmic story that has been unfolding for billions of years and will continue to unfold for billions more. As we continue to explore the mysteries of Laniakea, we are also learning more about the fundamental laws of physics that govern the universe. From the behavior of gravity to the role of dark matter and dark energy, the study of superclusters like Laniakea is pushing the boundaries of our knowledge and challenging our understanding of the cosmos. And as our observational technologies continue to improve, we are likely to uncover new and surprising details about the structure and evolution of the universe. The discovery of Laniakea itself was a groundbreaking achievement, one that required the combined efforts of astronomers, physicists, and mathematicians from around the world. Using advanced mapping techniques and sophisticated computer models, scientists were able to trace the movements of galaxies across vast distances, revealing the hidden structure of the universe. This discovery was the result of decades of research and collaboration, and it has opened up new avenues for understanding the cosmos. One of the key tools in the study of superclusters like Laniakea is the use of large-scale surveys. These surveys, conducted by telescopes such as the Sloan Digital Sky Survey (SDSS), have allowed astronomers to map the positions of millions of galaxies across the sky. By analyzing the distribution of galaxies, scientists can identify patterns and structures that reveal the underlying architecture of the universe. These surveys have played a crucial role in uncovering the existence of Laniakea and other superclusters, and they continue to provide valuable data for researchers studying the large-scale structure of the cosmos. In addition to large-scale surveys, astronomers also use simulations to model the behavior of galaxies and superclusters. These simulations take into account a variety of factors, including gravity, dark matter, and the expansion of the universe, to create realistic models of how galaxies move and interact over time. By comparing these simulations to actual observations, scientists can refine their understanding of the forces that shape the universe and test different hypotheses about the future of superclusters like Laniakea. The study of Laniakea also highlights the importance of international collaboration in the field of astronomy. The discovery of this supercluster was made possible by the collective efforts of scientists from many different countries, each contributing their expertise and resources to the project. This collaboration is essential for advancing our understanding of the universe, as the questions we seek to answer are often too complex and vast for any one group of researchers to tackle alone. As we continue to study Laniakea and other superclusters, we are uncovering new insights into the nature of the cosmos. Each discovery brings us one step closer to understanding the fundamental forces that govern the universe and the processes that have shaped its structure. The mysteries of Laniakea, from the enigmatic great attractor to the influence of dark matter and dark energy, are just the beginning. As we look to the future, we can only imagine what new revelations await us in the vast, interconnected expanse of the universe. The story of Laniakea is a story of discovery, exploration, and the unrelenting pursuit of knowledge. It is a reminder that the universe is far more complex and mysterious than we can ever fully comprehend. But it is also a testament to the power of human curiosity and ingenuity, and the incredible potential for scientific discovery that lies ahead. As we continue to explore the vast expanse of space, we are not just uncovering the secrets of Laniakea, but also learning more about our place in the grand cosmic tapestry and the profound mysteries that lie beyond. As we look toward the future of space exploration, one thing is clear: the mysteries of Laniakea and the universe as a whole are far from being solved. While we have made significant strides in understanding the structure of our supercluster and its place in the larger cosmic landscape, there is still so much left to learn. As technology continues to advance, we may find new ways to observe distant galaxies, uncover hidden patterns in the cosmic web, and unlock the secrets of dark matter and dark energy. One of the most exciting areas of research is the study of the cosmic web, the vast network of interconnected galaxies, clusters, and superclusters that make up the large-scale structure of the universe. Laniakea is just one part of this intricate structure, which spans billions of light-years. The cosmic web is a dynamic and ever-evolving system, with galaxies flowing along invisible threads of dark matter. By studying the motion of galaxies within Laniakea and other superclusters, scientists are beginning to uncover the true nature of this cosmic network and how it has evolved over time. The cosmic web is not just a theoretical concept. It has been observed in great detail using powerful telescopes and advanced computer simulations. These observations have revealed that the universe is not uniformly distributed. Instead, galaxies tend to cluster together in vast superclusters, separated by enormous voids of empty space. These superclusters are like the nodes of a giant cosmic network, connected by long, thin filaments of galaxies and dark matter. The study of these filaments, known as the cosmic strands, is a key area of research in modern cosmology. Laniakea itself is a prime example of how galaxies are connected in this cosmic web. Its intricate structure, with galaxies flowing towards the Great Attractor and interacting with nearby superclusters, is just one small part of the larger picture. By studying Laniakea and other superclusters, scientists can begin to piece together the larger puzzle of how the universe has evolved and how the cosmic web came to be. As we continue to explore the cosmic web, we are also learning more about the fundamental forces that shape the universe. For example, the role of dark matter in the formation and evolution of superclusters is still not fully understood. Dark matter, which makes up a significant portion of the universe's mass, has a profound influence on the motion of galaxies. It acts as a kind of scaffolding, providing the gravitational pull that keeps galaxies together and shapes their interactions. Yet, despite its importance, dark matter remains elusive, with scientists still unsure about its true nature. Dark energy, on the other hand, is an even more mysterious force. This invisible energy is responsible for the accelerated expansion of the universe. It has been detected through its effects on distant galaxies, but its precise properties are still unknown. As the universe continues to expand at an accelerating rate, the role of dark energy in the evolution of superclusters like Laniakea becomes increasingly important. Will dark energy continue to drive the expansion of the universe, or will its effects eventually slow down? These are questions that cosmologists are actively working to answer. Another exciting aspect of the study of Laniakea is the potential for discovering new galaxies and structures within it. While we have mapped out many of the galaxies within our supercluster, there are likely many more that remain hidden from view. The vastness of space means that even the most powerful telescopes can only observe a small fraction of the universe at any given time. As our observational technologies improve, we may discover new regions of Laniakea that are currently invisible to us. These discoveries could reveal new insights into the formation of superclusters and the processes that govern the movement of galaxies. One of the most promising tools for uncovering hidden galaxies is the next generation of space telescopes. The James Webb Space Telescope, scheduled for launch in the near future, is expected to provide unprecedented views of the universe, including distant galaxies within Laniakea. This telescope, with its advanced infrared capabilities, will allow scientists to observe galaxies that are too faint or distant to be seen by current telescopes. By studying these galaxies, we may gain new insights into the early history of the universe and the formation of superclusters like Laniakea. In addition to the James Webb Space Telescope, there are also plans to launch other space missions that will help us explore the universe in greater detail. For example, the Euclid mission, set to launch in the coming years, will focus on studying the geometry of the universe and the effects of dark energy. By mapping the distribution of galaxies and superclusters, Euclid will provide valuable data on the large-scale structure of the universe and help us understand the role of dark energy in the expansion of space. As our understanding of Laniakea and the cosmic web deepens, we will also gain new insights into the fundamental nature of space, time, and gravity. The study of superclusters like Laniakea is not just about mapping the distribution of galaxies. It is also about understanding the very fabric of the universe itself. How do galaxies move through space? What are the forces that govern their motion? And how did the universe come to be the way it is today? These are questions that have fascinated scientists for centuries, and with each new discovery, we are one step closer to finding answers. The study of Laniakea is a crucial part of this quest, as it provides a window into the large-scale structure of the universe and the forces that shape it. By continuing to explore the mysteries of Laniakea, we are not only learning more about our own cosmic neighborhood but also about the fundamental nature of the cosmos itself. As we continue to explore space and uncover the mysteries of the universe, one thing is certain: the story of Laniakea and the cosmic web is far from over. There are still countless discoveries to be made, and with each new revelation, we come closer to understanding the true nature of the universe and our place within it. Whether through the study of galaxy clusters, the search for hidden galaxies, or the exploration of dark matter and dark energy, the journey of discovery is just beginning. And as we look toward the future, we can only imagine the amazing insights that await us in the vast expanse of space. The study of Laniakea and the larger cosmic web is a reminder of the immense scale and complexity of the universe. It is a reminder that we are just one small part of a vast, interconnected network of galaxies, each playing a role in the ongoing evolution of the cosmos. And as we continue to explore the mysteries of space, we are reminded that there is still so much to learn, so much to discover, and so much more to understand about the universe that surrounds us. As we look deeper into the cosmos, one of the most compelling aspects of studying the Laniakea Supercluster is understanding its relationship with other superclusters and the broader framework of the universe. While Laniakea is a massive structure, it is far from the only one. In fact, it is part of an even larger cosmic network, connected to other superclusters and structures by the vast, unseen threads of dark matter and the effects of gravity. The interactions between these superclusters, as well as the gravitational influence they exert on each other, can help us understand the larger dynamics of the universe. One of the most intriguing phenomena that scientists are currently investigating is the movement of superclusters themselves. It's not just that galaxies move within superclusters; the superclusters themselves are moving through space as well. This phenomenon is part of a larger cosmic process known as the flow of the universe. Essentially, superclusters, including Laniakea, are being pulled toward one another, influenced by gravitational forces. This cosmic flow is guided by the distribution of matter throughout the universe, including the mysterious dark matter that cannot be directly observed but exerts a tremendous gravitational effect on visible matter. The movement of superclusters has profound implications for our understanding of the universe's evolution. In the distant past, these superclusters were more spread out, but as the universe ages, the gravitational pull between them causes them to move closer together. This process could eventually lead to even larger cosmic structures, as smaller superclusters merge to form even more massive ones. As these superclusters collide, they will likely cause a chain reaction, affecting the galaxies within them. Understanding the long-term fate of superclusters like Laniakea could give us insight into the far future of the universe, including how it will continue to evolve. At the heart of this cosmic motion lies dark energy, an invisible force driving the accelerated expansion of the universe. Dark energy has been a subject of intense study for decades, and its influence is evident not just in the movement of galaxies and superclusters, but in the overall shape and fate of the universe itself. While dark matter is thought to play a critical role in forming and holding together galaxies, dark energy is believed to work in opposition, pushing the universe apart at an ever-accelerating rate. The study of these forces within Laniakea and other superclusters will be crucial for advancing our understanding of how the universe began, how it will evolve, and what its ultimate fate may be. For instance, we know that dark energy's influence is causing galaxies to move away from each other at an accelerating pace. As this expansion continues, it could eventually lead to the Big Freeze, a scenario in which galaxies, stars, and even atoms become so far apart that the universe becomes cold, dark, and lifeless. Alternatively, there is a possibility that the expansion of the universe could slow down and reverse, leading to a big crunch, in which everything collapses back together. These competing theories hinge on our understanding of forces like dark energy and the intricate motions of structures like superclusters. Moreover, the movements of galaxies within the superclusters of Laniakea provide a unique opportunity to study the nature of gravity itself. As we observe how galaxies interact with each other within this supercluster, we gain more data on gravitational forces across vast distances. The movements of these galaxies and their interaction with the surrounding dark matter can help us refine our models of gravity. Will we discover new, unknown forces at work? Or is gravity, as we know it, a reliable force over the immense scales of space and time? This remains an open question that can only be answered through continued observation and research. A fascinating aspect of Laniakea's structure is its central region, where the Great Attractor is located. This is a massive and mysterious concentration of mass that exerts an enormous gravitational pull on galaxies within Laniakea. The Great Attractor itself remains elusive, hidden behind the dense plane of the Milky Way, but its gravitational effects are undeniable. It's as if this invisible force is tugging on the galaxies in the region, directing them in a cosmic dance that spans millions of light years. Understanding the Great Attractor could unlock new insights into the distribution of mass in the universe and offer clues about the mysterious dark matter that is believed to make up a significant portion of the universe's mass. However, the Great Attractor is just one part of the puzzle. As we peer farther out into the universe, we realize that there are other superclusters, some larger than Laniakea, others with unique properties that could challenge our understanding of cosmic structure. Some of these superclusters are connected to one another by vast filaments of dark matter, forming a cosmic web that spans unimaginable distances. The study of these connections could reveal new insights into the role of dark matter, dark energy, and the gravitational forces that shape the large-scale structure of the universe. One of the most recent developments in the study of the Laniakea Supercluster is the use of advanced simulation techniques to model its formation and evolution. By simulating the movement of galaxies, dark matter, and other cosmic components, scientists can gain a deeper understanding of the forces at work. These simulations are constantly improving, incorporating new data from telescopes, observatories, and space missions. As technology advances, simulations will become even more precise, allowing us to explore the universe in greater detail than ever before. Moreover, as our observational capabilities improve, we may uncover hidden aspects of Laniakea and its surrounding regions. For example, there could be galaxies and structures deep within the supercluster that are currently obscured by dust or other cosmic phenomena. The use of infrared and radio telescopes, such as the upcoming James Webb Space Telescope, will allow scientists to peer through these cosmic obstacles, revealing new details about the universe's largest structures. Laniakea, as a supercluster, also provides a critical test for some of the most fundamental theories in cosmology. For example, the Lambda-CDM model, which is the standard model of cosmology, predicts the existence of large structures like Laniakea. By studying these superclusters and their properties, scientists can test the validity of this model and refine it if necessary. New discoveries within Laniakea could lead to a rethinking of some of our assumptions about the universe, possibly even introducing new theories that challenge our current understanding. In a more philosophical sense, the study of Laniakea offers us an opportunity to reflect on our place in the cosmos. As we learn more about the vastness of the universe and the superclusters that populate it, we come to understand how small and interconnected our own galaxy truly is. Laniakea serves as a reminder that we are part of something much larger than ourselves, a cosmic web that stretches across billions of light years. As we explore this vast network, we gain a deeper appreciation for the beauty and complexity of the universe, and for the endless mysteries that remain to be unraveled. And as we look toward the future, the possibilities are endless. With each new discovery, whether through powerful telescopes, advanced simulations, or groundbreaking theories, we move closer to understanding the true nature of Laniakea and its place in the grand tapestry of the cosmos. As our knowledge of the universe expands, we will continue to ask the fundamental questions about space, time, and the very forces that govern our existence. What lies beyond Laniakea? What secrets remain hidden in the far reaches of the universe? And what new mysteries will emerge as we continue to explore the cosmos? The journey of discovery is far from over. The study of the Laniakea Supercluster is just one chapter in the ongoing exploration of the universe. With each new piece of knowledge, we move closer to answering some of the greatest questions of our time. What we discover next could change the way we view the cosmos forever. As we continue to explore the depths of the Laniakea Supercluster, we begin to see that this immense structure is not only a vital part of our galactic neighborhood but also an essential piece in understanding the larger cosmic puzzle. In fact, the more we learn about Laniakea, the more it becomes apparent that it is part of a much larger, complex system of interconnected galactic structures that stretches across the universe. To truly understand the implications of Laniakea, we must also explore the larger cosmic web and the relationships between superclusters, galaxies, dark matter, and dark energy. At the most fundamental level, the Laniakea Supercluster is made up of thousands of galaxies, including the Milky Way, that are bound together by gravitational forces. However, the vast majority of the mass in this supercluster is not visible to the naked eye. Instead, it is composed of dark matter, which cannot be directly observed but is inferred through its gravitational effects on visible matter. Dark matter plays a critical role in the formation and maintenance of galactic structures, providing the gravitational pull that holds galaxies and superclusters together. Dark matter, despite being invisible and mysterious, is thought to make up roughly 27% of the universe's total mass energy content. It is essential for the stability of large structures like the Laniakea Supercluster. Without dark matter, the galaxies within Laniakea would not be able to stay gravitationally bound to one another, and the entire supercluster would break apart. This invisible substance is responsible for the bulk of the gravitational forces that maintain the cohesion of the supercluster and ensure that it continues to move and evolve in a relatively stable way. However, dark matter is not the only mysterious substance that affects the Laniakea Supercluster. Dark energy, which is thought to make up around 68% of the universe's total energy content, plays an equally crucial role. Dark energy is the force driving the accelerated expansion of the universe. Its effects are evident not just on the scale of individual galaxies, but on the scale of superclusters like Laniakea. Dark energy works in opposition to gravity, pushing galaxies and superclusters apart at an ever-increasing rate. The interplay between dark matter, dark energy, and gravity is what governs the large-scale structure of the universe. In the case of Laniakea, dark matter is responsible for binding galaxies together, while dark energy is pulling them apart. The combination of these forces creates a dynamic tension that shapes the evolution of superclusters, determining how they form, grow, and interact with one another. As scientists continue to study the Laniakea Supercluster, they are gaining new insights into how these forces work together. The study of the cosmic web, the network of superclusters and other large-scale structures that make up the universe, is helping scientists develop new models of cosmic evolution. These models aim to explain how the universe's vast structures came to be and how they will evolve in the future. One of the key tools for studying these large-scale cosmic structures is computer simulations. By modeling the behavior of galaxies, dark matter, and dark energy, scientists can simulate the evolution of the universe over billions of years. These simulations are helping us understand how superclusters like Laniakea form and evolve over time. They also give us insight into the future of these structures, providing a glimpse into what the universe might look like millions or even billions of years from now. For example, simulations have shown that superclusters like Laniakea are not static entities. They are constantly evolving, with galaxies moving in response to the gravitational pull of dark matter and dark energy. Over time, these galaxies will continue to drift and interact with one another, potentially merging to form even larger galactic structures. Some of these interactions will be violent, leading to the formation of new stars, the destruction of old ones, and the eventual birth of new galaxies. As we look to the future, one of the most pressing questions about the Laniakea Supercluster is its fate. Will it continue to evolve and grow, or will it eventually be torn apart by the forces of dark energy? The current accelerated expansion of the universe suggests that superclusters like Laniakea will continue to move farther apart, but this does not mean that they will cease to interact. Even as galaxies and superclusters move away from each other, they will still feel the gravitational pull of neighboring structures, leading to a complex and ever-changing cosmic dance. In the distant future, as the universe continues to expand, it is possible that Laniakea will eventually break apart. However, this process could take billions of years, and it is difficult to predict the precise outcome. It is also possible that, in the far future, the accelerated expansion of the universe could slow down, leading to a dramatic reversal in the movement of galaxies and superclusters. Such a reversal could bring Laniakea and other superclusters closer together, potentially leading to a cosmic, Big Crunch, where all the matter in the universe collapses in on itself. Despite these uncertainties, the study of Laniakea offers us a unique opportunity to explore the forces that shape the universe. By studying the movement of galaxies within the supercluster, scientists are gaining valuable insights into the nature of gravity, dark matter, and dark energy. These insights could have profound implications for our understanding of the universe, not just in the present but in the distant future as well. As we continue to observe and study the Laniakea Supercluster, new technologies and techniques will undoubtedly lead to more discoveries. For instance, the upcoming James Webb Space Telescope, which is designed to observe infrared light, will allow scientists to peer deeper into the universe than ever before. This telescope will provide us with more detailed images of distant galaxies, allowing us to study their properties and movements within the supercluster. By observing the galaxies within Laniakea, we can gain more information about how they interact with one another and with the dark matter and dark energy that shape the supercluster. In addition to observational tools like the James Webb Space Telescope, advances in computational modeling will continue to play a crucial role in our understanding of Laniakea and other superclusters. These models will allow scientists to simulate the evolution of the universe on ever larger scales, providing insights into the interactions between galaxies, superclusters, and dark matter. As our ability to simulate the universe improves, we will be able to answer more questions about the structure and fate of the cosmos. At the same time, as we delve deeper into the study of the Laniakea Supercluster, we must also recognize the philosophical implications of our findings. The more we learn about the vastness and complexity of the universe, the more we are confronted with questions about our place in it. Are we truly alone in the universe, or is life more widespread than we can imagine? How did the universe come into being, and how will it evolve in the future? These questions remind us that the study of the cosmos is not just about discovering new facts and theories. It is also about exploring the fundamental mysteries of existence itself. As we continue to probe the depths of space and uncover the secrets of structures like the Laniakea Supercluster, we are not only advancing our knowledge of the universe, we are also confronting the deeper questions about life, matter, and the nature of reality. In the coming years, as our observational tools and theoretical models continue to improve, we can expect even more exciting discoveries about the Laniakea Supercluster and the larger universe it is part of. From the mysteries of dark matter and dark energy to the future evolution of superclusters, there is still much to learn. What we discover in the future could radically change our understanding of the universe, shedding new light on the forces that govern everything from the smallest particles to the largest cosmic structures. As we move forward into this era of discovery, one thing is certain: the study of the Laniakea Supercluster and the broader cosmos will continue to captivate our imaginations and challenge our understanding of the universe. Whether we are looking to the past to understand the origins of the supercluster or to the future to predict its eventual fate, the journey of discovery is far from over. With each new discovery, we are one step closer to unlocking the greatest mysteries of the universe. As we continue to unravel the mysteries of the Laniakea Supercluster and its place within the larger cosmos, we must also recognize the limitations of our current understanding. Despite the groundbreaking discoveries made so far, the sheer complexity and scale of structures like Laniakea continue to pose challenges for scientists. It's one thing to observe galaxies and clusters and another to fully comprehend the underlying forces that shape them. The more we explore, the more we realize that the universe is full of unknowns, and each discovery leads to more questions than answers. One of the biggest challenges in studying structures like the Laniakea Supercluster is the immense distances involved. Even the closest galaxies within the supercluster are separated by millions of light years. A light year, the distance that light travels in 1 year, is roughly 5.88 trillion miles, 9.46 trillion kilometers. This means that when we observe a galaxy in Laniakea, we are looking at light that left that galaxy millions or even billions of years ago. In other words, when we study the supercluster, we are essentially looking back in time. This makes it incredibly difficult to study the present state of these galaxies, as we are often seeing them as they were in the distant past. In addition to the challenge of distance, there is also the issue of the vastness of Laniakea itself. As we've discussed, this supercluster spans over 500 million light-years. The sheer size of the supercluster makes it difficult to study its full extent, and even the most advanced telescopes and observational techniques can only provide us with a limited view of the universe. The James Webb Space Telescope, for example, while providing unparalleled views of the universe, will still only be able to observe a fraction of the galaxies within Laniakea. To truly map the entire supercluster and understand its structure, we would need a much more comprehensive approach, combining data from multiple telescopes and observational techniques. Yet, despite these challenges, the progress we've made so far is nothing short of remarkable. As we learn more about the Laniakea Supercluster, we are also learning more about the universe as a whole. The discovery of the supercluster has opened new avenues of research into the large-scale structure of the cosmos. The more we understand about Laniakea, the better equipped we are to study other superclusters and galactic structures. By studying the formation and evolution of Laniakea, we can make predictions about how other superclusters might behave over time. Perhaps one of the most exciting aspects of studying the Laniakea Supercluster is its potential to reveal clues about the overall structure and fate of the universe. As we mentioned earlier, the universe is expanding, and this expansion is accelerating due to the influence of dark energy. While we cannot yet fully comprehend the long-term effects of this accelerated expansion, the study of superclusters like Laniakea could provide us with vital clues about what the future holds. Will the universe continue to expand indefinitely, eventually resulting in a cold, dark, and empty cosmos? Or will it one day slow down and reverse, leading to a big crunch, where everything collapses back in on itself? By observing the motion of galaxies within superclusters like Laniakea, we may be able to better understand the forces at play and gain insight into the ultimate fate of the universe. Another fascinating possibility is that the Laniakea Supercluster might hold the key to understanding the mysterious phenomenon known as cosmic voids. These voids are vast regions of space that contain very few galaxies, making them appear as empty spaces between the large cosmic structures. Voids are often found in the spaces between superclusters, and they are thought to be the result of the gravitational pull exerted by the galaxies within the superclusters. While we know that voids exist, their formation and evolution remain a mystery. The study of Laniakea could help us understand how voids are created and what role they play in the larger structure of the universe. As we look beyond the Laniakea Supercluster to other superclusters in the universe, we are also confronted with the question of how these structures interact with one another. While we often think of galaxies and superclusters as isolated entities, they are part of a much larger cosmic web. This web is made up of filaments of galaxies and dark matter that stretch across the universe, connecting superclusters to one another in a vast network. The interaction between these filaments and the movement of galaxies within them can provide valuable information about the overall structure of the universe. For example, the movement of galaxies within Laniakea is influenced not only by the gravitational pull of dark matter but also by the cosmic web's larger structure. As galaxies move through the supercluster, they are also influenced by the gravitational effects of neighboring superclusters and filaments. This interconnectedness means that the evolution of one supercluster can have ripple effects on the entire cosmic web. In the case of Laniakea, understanding how galaxies within the supercluster interact with neighboring superclusters and filaments could provide us with valuable information about the dynamics of the entire cosmic network. The study of superclusters and their interactions is also helping to shed light on the nature of dark matter and dark energy. These mysterious substances, which make up the vast majority of the universe's mass and energy, have been the subject of intense study for decades. While scientists have made significant strides in understanding the properties of dark matter and dark energy, many questions remain. By observing how dark matter and dark energy influence the movement of galaxies within superclusters like Laniakea, scientists are gaining new insights into their behavior and how they shape the structure of the universe. For instance, the study of how galaxies move within the Laniakea Supercluster could help scientists understand the distribution of dark matter. As galaxies move through the supercluster, they experience the gravitational pull of dark matter, which affects their velocity and trajectory. By analyzing the movement of galaxies within Laniakea, scientists can map the distribution of dark matter and gain new insights into its properties. Similarly, the study of dark energy's effects on the supercluster can provide valuable clues about the nature of this mysterious force and its role in the accelerated expansion of the universe. As we continue to observe and study the Laniakea Supercluster, new discoveries will undoubtedly be made. Whether through new telescopes, advanced simulations, or novel observational techniques, the future of Laniakea research holds tremendous promise. In the coming decades, we may learn more about the supercluster's past, present, and future, gaining a deeper understanding of its place in the vast expanse of the universe. The study of the Laniakea Supercluster and the cosmic web is not just about understanding the structure of the universe. It is about answering some of the most fundamental questions about existence itself. What is the nature of dark matter and dark energy? How did the universe come to be, and how will it evolve? By answering these questions, we are not only unraveling the mysteries of Laniakea, but we are also uncovering the secrets of the universe as a whole. The more we learn about Laniakea and the forces that shape it, the closer we come to understanding the ultimate nature of reality. From the largest superclusters to the smallest particles, every discovery brings us one step closer to unlocking the greatest mysteries of the cosmos. And as we continue this journey of exploration and discovery, one thing is certain: the story of the Laniakea Supercluster is far from over. The vast and intricate nature of the Laniakea Supercluster not only illuminates the larger cosmos but also underscores our own place within the universe. When you think about our Milky Way galaxy within the context of Laniakea, it becomes astonishing to realize how minuscule and fleeting our existence is within such a colossal structure. It's a humbling thought, reminding us of the incredible scope of the universe and our constant journey to understand it. While the Laniakea Supercluster is undoubtedly the most important supercluster we can study, it also serves as a gateway to understanding other superclusters in the universe. Researchers are beginning to study other superclusters, such as the Shapley Supercluster, which is roughly 650 million light-years away from us, and the Persis-Pisces Supercluster, which stretches across 100 million light-years. The patterns we observe in Laniakea might reveal similar structures, behaviors, and dynamics in other clusters that can shed light on the universal principles that govern galaxy clusters, dark matter, and cosmic evolution. In essence, Laniakea acts as a model for understanding not only our immediate surroundings but also the cosmic web that connects all superclusters. In understanding Laniakea, it's worth considering the way these superclusters are structured. If we think about the universe as a giant network, superclusters like Laniakea are the major nodes, with galaxies and galaxy clusters connecting these nodes in vast, web-like structures. This network, known as the cosmic web, is an intricate framework of dark matter and galaxies, stretching across the entire observable universe. The cosmic web provides the backbone of structure within the universe, dictating how galaxies and galaxy clusters form, evolve, and interact. One of the most fascinating aspects of the cosmic web is the role of dark matter. Dark matter is thought to make up about 85% of the total mass of the universe, yet it remains invisible and undetectable by conventional means. Its gravitational influence, however, is undeniable. Dark matter is believed to form the underlying structure of the cosmic web, providing the scaffolding that galaxies and clusters of galaxies form around. It's dark matter that causes the galaxies within superclusters like Laniakea to move in the ways that we observe today. Understanding the distribution of dark matter in Laniakea and beyond will undoubtedly unlock many more secrets of the universe's formation and evolution. Furthermore, the study of the Laniakea Supercluster helps to broaden our understanding of how galaxies interact with one another. While galaxies are often thought of as isolated entities, they are in fact engaged in complex interactions with their neighbors. These interactions can take many forms. Galaxies can collide, merge, or simply pass by each other, influencing each other's structure and evolution. Within the Laniakea Supercluster, there is a vast network of galaxy clusters, and each galaxy within those clusters is constantly interacting with its neighbors. Over billions of years, these interactions have led to the formation of galaxy clusters, as well as the occasional galaxy merger, which can trigger the birth of new stars or even lead to the formation of supermassive black holes. The dynamics within these galaxy clusters also play a crucial role in the behavior of galaxy clusters across the universe. In Laniakea, as well as in other superclusters, the galaxies are bound together by gravity, forming gravitationally bound groups called galaxy clusters. The movement of galaxies within these clusters is affected by a number of factors, including the influence of dark matter, the distribution of gas and dust, and the relative velocities of the galaxies themselves. As galaxies move through the cluster, they are subject to gravitational interactions that can alter their trajectories and even cause them to collide or merge. These collisions and mergers can have dramatic consequences, sometimes triggering the formation of new stars, altering the shape of galaxies, or even causing the birth of supermassive black holes. But beyond just the mechanics of galaxy formation and interaction, the Laniakea Supercluster also provides crucial clues about the cosmic forces that shape the universe itself. The study of the supercluster's overall motion and expansion can help to inform our understanding of dark energy, the mysterious force responsible for the accelerated expansion of the universe. Laniakea's motion, particularly the way its galaxies are moving away from each other, could provide valuable insights into how the universe itself will evolve in the future. It's important to recognize that the Laniakea Supercluster isn't the end of the road in the cosmic landscape. While it's one of the largest and most significant structures we've discovered, we are only scratching the surface of understanding the full extent of the cosmic web. There are likely other superclusters, some even larger than Laniakea, lurking out there in the universe, waiting to be discovered. And as technology advances, so too will our ability to observe and understand these distant structures. With the development of future telescopes like the Extremely Large Telescope, ELT, and even more powerful space observatories, our ability to map the universe and study its largest structures will only improve. What's more, the study of superclusters like Laniakea is helping to advance other fields of astronomy and physics. For example, the study of galaxy clusters can provide valuable information about the nature of galaxy formation and evolution, which can help scientists understand how galaxies like our own Milky Way came to be. Similarly, studying the cosmic web and the distribution of dark matter can help researchers gain a better understanding of the overall shape and structure of the universe, as well as the forces that govern its expansion. The insights we gain from Laniakea and other superclusters will undoubtedly influence many areas of scientific inquiry and help to shape our understanding of the universe as a whole. Moreover, the more we learn about superclusters, the more we realize that our understanding of the universe is still in its infancy. As we push the boundaries of our knowledge, we are faced with an ever-growing list of questions. How did the supercluster form? What is the true nature of dark matter and dark energy? How do the large-scale structures of the universe interact with one another? These are just a few of the questions that remain unanswered, and they drive the ongoing quest to uncover the secrets of the cosmos. Yet, despite the unanswered questions, the progress made in the study of Laniakea and other superclusters is undeniably impressive. The discovery of Laniakea has changed the way we think about the universe, showing us that our galaxy is not isolated, but rather part of an enormous, interconnected network of galaxies. This realization has profound implications for our understanding of the universe and our place within it. It also highlights the power of human ingenuity and collaboration in advancing our knowledge. By pooling together data from observatories around the world and using advanced computational models, scientists have been able to map out the intricate structure of the Laniakea Supercluster and gain new insights into the universe's largest structures. And so, the study of the Laniakea Supercluster is far from over. As we continue to observe, explore, and learn, we will undoubtedly uncover even more about this vast and awe-inspiring structure. And in doing so, we will continue to peel back the layers of the universe, revealing more of its mysteries, and perhaps, just perhaps, learning a little more about our place within it. The quest to understand Laniakea and other superclusters is not just about charting the cosmos. It's a pursuit to grasp the very fabric of the universe itself, its origins, its structure, and its future. The mysteries hidden within these superclusters offer more than just a glimpse into the vastness of space. They provide answers to some of the most fundamental questions that have puzzled humanity for centuries. What is the universe made of? How did it come to be? And, ultimately, where is it headed? To delve deeper into the significance of Laniakea, we must also consider its connection to the larger scale of cosmic history. The formation of superclusters like Laniakea is not an isolated event. It is part of an ongoing process that began with the Big Bang itself, roughly 13.8 billion years ago. In the aftermath of the Big Bang, matter was scattered across the universe in a nearly uniform distribution, but over time, small fluctuations in density led to the formation of stars, galaxies, and eventually, the enormous structures we see today, like Laniakea. These fluctuations in density, driven by the fundamental forces of gravity and dark matter, created a blueprint for the cosmic web, the vast network of galaxies, clusters, and superclusters that define the structure of the universe. Understanding Laniakea's role within this context sheds light on how the universe has evolved over billions of years. In the early universe, the first galaxies began to form from dense pockets of gas and dark matter. These early galaxies merged and interacted, eventually forming larger clusters. Over time, these clusters grew into superclusters, and today, Laniakea stands as one of the largest known superclusters in the observable universe. This process of galaxy formation, merging, and clustering continues even now, with new galaxies and superclusters being born as the universe expands. One key aspect of Laniakea's formation is the role of dark matter. Dark matter, which accounts for a significant portion of the universe's mass, plays a central role in shaping the structure of the cosmos. Although it is invisible and cannot be directly observed, scientists have deduced its existence based on its gravitational effects on visible matter. Dark matter's influence is most noticeable in galaxy clusters and superclusters, where it acts as a cosmic glue, binding galaxies together and preventing them from flying apart due to their high velocities. Without dark matter, the formation of superclusters like Laniakea would be nearly impossible. In addition to dark matter, the expansion of the universe itself is a crucial factor in the formation of superclusters. The discovery of the universe's accelerated expansion, driven by dark energy, has transformed our understanding of the cosmos. Dark energy is a mysterious force that counteracts gravity and causes the universe to expand at an ever-increasing rate. This acceleration is not only influencing the large-scale structure of the universe but also dictating how superclusters like Laniakea evolve. As galaxies within Laniakea move apart due to the expansion of the universe, they are also being influenced by the gravitational pull of other galaxies within the supercluster, which causes them to move toward one another. This delicate balance between expansion and gravitational attraction will ultimately shape the future of Laniakea and other superclusters. Looking ahead, the study of Laniakea provides important clues about the universe's fate. The cosmic expansion, driven by dark energy, is expected to continue indefinitely, leading to a future where galaxies become increasingly distant from one another. This ongoing expansion will likely result in a cosmic isolation, where galaxies no longer interact or collide as they did in the past. The future of Laniakea, like other superclusters, will depend on how it continues to evolve in response to this expansion. Some researchers speculate that Laniakea and other superclusters may eventually become isolated islands in a vast, expanding universe, with no further interactions between them. But while the future of Laniakea may involve cosmic isolation, the history and formation of superclusters like it are far from static. As we continue to refine our observations and develop new technologies, we will gain an even deeper understanding of these vast structures. New observations using cutting-edge telescopes and data from observatories around the world will help us map the universe with greater accuracy, revealing details about Laniakea and other superclusters that were previously hidden from view. The discovery of new superclusters, along with a more detailed understanding of dark matter and dark energy, will provide crucial insights into the fundamental forces that govern the universe. Moreover, the study of Laniakea is not just about understanding the large-scale structure of the universe. It is also about better understanding the galaxy we call home, the Milky Way. As part of Laniakea, the Milky Way is deeply connected to the larger cosmic network. Studying how our galaxy interacts with other galaxies in the supercluster will help scientists better understand its past, present, and future. For example, the movement of the Milky Way and its neighboring galaxies within Laniakea is influenced by the gravitational pull of other galaxies, as well as the overall motion of the supercluster itself. By tracking these movements, scientists can gain insights into the evolution of our galaxy, its relationship with neighboring galaxies, and the cosmic forces that have shaped its history. Additionally, the study of Laniakea may also have implications for our understanding of the formation of life. The cosmic environment in which a galaxy exists plays a crucial role in the development of life within it. Factors such as the rate of star formation, the presence of heavy elements, and the overall stability of the galaxy's environment all influence the conditions that make life possible. By studying Laniakea and its constituent galaxies, scientists may uncover new insights into the conditions necessary for the emergence of life, and whether those conditions might exist elsewhere in the universe. As we push the boundaries of our knowledge and technology, the Laniakea Supercluster will continue to serve as a focal point for research and discovery. Its vastness and complexity challenge us to think beyond the familiar, urging us to consider the universe in its grandest scale. The more we learn about Laniakea, the more we realize that the cosmos is an intricate and ever-evolving network, shaped by both known and unknown forces. It is a reminder of how much we still have to learn and how much wonder remains to be discovered. In the end, the Laniakea Supercluster is more than just a distant cluster of galaxies. It is a symbol of humanity's boundless curiosity and our desire to understand the universe. It represents the ongoing journey to explore the cosmos, a journey that will continue to unfold as we push the limits of our knowledge and technology. And in this vast and mysterious expanse, we are but a tiny speck, connected to every galaxy, every star, and every planet by the very forces that shape the universe itself. The more we learn about Laniakea, the more we learn about ourselves, and the more we realize how much there is yet to discover. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.